Hello students, welcome to the crash course of this 40 days, and today we will be covering the day 28. Now, today's chapter would be general organic chemistry. In yesterday's class, we have talked about the general organic chemistry. Now, today we will look upon the nomenclature primarily. Okay, so this is our disclaimer. As I said earlier, we will discuss the IUPAC system. So, you already know that in the trivial system, name was assigned according to the discoverer, and there was no such concrete system for naming the compounds. Now, this created a lot of ambiguity. To remove this ambiguity, what we did, we structured a proper way to name any organic compound. And what was the name of that structure? So, it was designed in 1957 by International Union of Pure and Applied Chemistry, and this is famous known as the IUPAC system of naming the organic compounds. Remember, this is the same IUPAC which has named the coordination compound, and the same IUPAC which has named the elements whose atomic number is greater than 100. Now, this IUPAC system is naming the compound particularly on the basis of its structure. Okay, so it has a set of rules, and you have to remember the rules in the chronicle order. Means you cannot play with the order. If the first rule is coming, you should look the compound according to the first rule, then apply the second rule, then the third rule, and then the fourth rule, and so on. You cannot apply it in a random manner. So this is very important to remember. So an IUPAC's name consists of prefixes and suffixes to indicate the substituents or functional group present in the compound. To define the main skeleton structure, we have the word root, which tells us about the length of the longest chain possible. Now, what are prefixes and what are suffixes? You must have heard this term in your grammar also. So, prefixes are something which are placed before the word, means it is coming before the word. So, we have some examples of prefixes like bi, di, tetra. So, these are kind of prefixes which are placed before the ligands in case of coordination chemistry to indicate their count in the given coordination compound. Similarly, we have suffixes. The suffixes are used generally for the primary functional group. We will come to know in the upcoming slides that what are primary functional group and what are secondary functional groups. But for the time being, you should try to understand that what does prefix indicate and what does suffix indicate. So you will see two types of things or species that would be attached to the main chain. First is the functional group. So we already talked a lot about this functional group. They are a group of atoms arranged in a certain pattern and their name is fixed. For example, we have carboxylic acid, we have aldehyde, and we have ketone. And then we have our substituents. The substituents are particularly your alkyl groups like your methyl, ethyl, isopropyl, butyl, and all. Now, in the systematic naming, which is the IUPAC nomenclature of organic compound, functional groups are typically indicated by suffixes. However, certain functional groups are never the principal functional group. So we always use suffixes for those functional groups which are having a higher priority. And for those functional group which has never been given a higher priority are always considered with the help of their prefixes. So what are those prefixes? First of all, let us start with the NO2 group, which is N double bond O and coordinate bond to the other oxygen, and its prefix is nitro. For example, if your alkane is methane, then NO2 attached to it will be named as nitromethane. Okay. Similarly, if your alkane is ethane and the NO2 group is attached to that ethane group, then in that case you will name it as nitroethane. After that, we have this OR. OR is basically consisted of a alkyl group attached to oxygen, and that oxygen in turn is attached to the main chain. So we use alkoxy prefix for this. So Here is a typical representation of an alkoxy, and you can clearly say that this is an example of ether. So ethers are oxygen containing compound in which oxygen is bonded to two different or same alkyl groups. Now, how you will name it? It is named as alkoxy alkane. So basically, we take the longest chain of the two alkyl groups, and the other one is named as alkoxy. Suppose there is a ethyl, then there is oxygen, and then there is a methyl. In that case, we will name it as methoxyethane. Got it? So we will take the longest chain as the alkane part and the smaller chain as the alkoxy part. After that, we have chloro as the next prefix for the halide known as chlorine. It's very simple. So there are four examples of it: chloroalkane, bromoalkane, iodoalkane, and fluoroalkane. You know it about the haloalkanes and haloarenes. So we'll study about this halogen there also. So remember, they have no suffix for them. They are only present in the form of prefixes. And lastly, we have this nitroso. Just remember that there is a very large difference between the nitro and the nitroso. So nitro means NO2 and nitroso means NO. But the rest part is same. You have to simply write it as nitro and then you have to write the name of the alkane. Suppose we have NO attached to a methane group. So we'll name it as nitrosomethane, or the next homologous series would be nitrosoethane. After that, we can have nitrosobutane, nitrosopentane. So you can easily get the consecutive homologous series by adding a CH2 unit, right? Remember, we have talked about the homologous series. So they are some group of elements, some group of compounds, I would say, not elements, which have the same functional group, or it can be an no functional group area. But the difference between two consecutive members will be of one CH2 unit. So that would change the molecular mass by 14U, because one carbon has an atomic mass of 12 and the two hydrogens have atomic mass of 1. I hope this part is clear to you. So the most important nomenclature in this whole scenario is your alkoxy 1, because we have a dedicated chapter for this, which is alcohol, phenol and ether, and there we will study about this ether group. And for ether, what do? We use the term alkoxy. So can we take more examples? Suppose we have a oxygen in middle, and on the right hand side we have a propyl group, on the left hand side we have a ethyl group. Then what would be the name? Its name would be ethoxypropane. Okay, so here what we have done, the alkane part is taken for the longest chain, which is your propane, and the alkoxy part is taken for the smaller one, which is your ethoxy. I hope this makes sense to you. So remember the names of the given functional group, and they will be always represented in the given compound with the help of their prefixes and never their suffixes. So if this is clear, we'll move on to the next part, which is regarding your secondary suffix. So we have two kinds of suffix. First one is primary suffix, and then we have secondary suffix. So primary suffix is the one which indicates the saturation of your carbon compound. So if it is having a double bond, then we will use our primary suffix as -ene, for triple bond -ine, and for single bond -ane. So these are the way to indicate your primary suffix, and they are used to indicate the saturation, that they are whether saturated or unsaturated. Now talking about the secondary suffix, it is mainly helpful in determining the primary functional group. Got it? So we will see this priority order in the upcoming slides, but before that you should remember their names, starting with the alcohol. So alcohol is indicated with the help of suffix ol. Suppose we have taken ethane and attached a hydroxy group to it, then it will be named as ethanol. Now imagine that we have two functional groups, and according to the priority order, your OH group or your alcohol group has a lower priority. In that case, you will use the prefix of alcohol and not the suffix. Now for that you should remember what is the prefix. So let me just tell it to you. You may note it down. For alcohol, the prefix is hydroxy and the suffix is ol. Got it? Moving on to the next, we have amines, which is written as NH2. Now here what we will do, we'll simply name it as alkanamine. So it can be methanamine, ethanamine, propanamine, butanamine, and so on. Now suppose your NH2 group is not acting as a primary functional group, okay, or your principal functional group, but a subsidiary functional group. So what you will do in that case, you will use your amine to be as a part of your prefix, okay. So you will represent the position of amines with the help of prefix. And what will be that prefix? It's very simple. You have to simply remove this E here and name it as amino, okay. So you will write it as amino, and then in the prefix part of the amino, you will indicate its position. Moving on to the next prefix, can you predict it? What is the prefix that is used for aldehyde? The suffix is given here and you know it very well, it is al. We have methanol, then we have ethanol, then we have propanol. But what is the prefix which is used for aldehyde? Anyone, can you tell me? Suppose your aldehydic group is not a part of the main functional chain, okay, or it is considered as a secondary or subsidiary functional group. So what is the prefix that will be used in the case of aldehyde? Can you tell me? Just write it in the comment section if you know about this. You may also write it for the upcoming ones like ketone, carboxylic acid, amides, acid halide. Okay, so let me tell it for you. The prefix which is used for aldehyde is formyl, Formyl. So we use the term formyl to represent the aldehyde in case it is a subsidiary functional group, and this will act as a prefix for the aldehyde. Then after we have the ketone. So we know it very well that ketone has ONE as the suffix, but if it is acting as a subsidiary functional group, its prefix will be oxo, right? Then after we have this carboxylic group. So it's very simple. It is depicted with the help of oic acid if it is acting as a primary functional group, or else we use the term carboxy, Carboxy. So carboxy is used. So you must have seen a ring. In the case of ring, we use this carboxy, 4 carboxy, 3 carboxy, to indicate the position of the carboxylic acid. Next we have amide. Now amide is named as alkanamide if it is acting as a primary functional group. So it can be methanamide, ethanamide, propanamide, and so on. But suppose it acts as a what? Secondary or subsidiary functional group. Then what is the prefix that we will use? Of course, you should remember that each time you see a functional group acting as a subsidiary or a secondary functional group, you will always use its prefix. So the prefix for this amide is amido. So similar to amine, by removing E, we can write our amide as amido, AMIDO. Then next we have acid halide. So we have talked about this functional group in the previous class also. It is a derivative of your carboxylic acid. So we can start from the amide, acid halide, ester, and and your say one more part was there which was about anhydride. So all of them are considered as the derivatives of carboxylic acid. So coming back to our discussion, in acid halide we have a halide group attached to the carbonyl carbon directly, and in that case we use the suffix oil halide. So it can be what, starting with the ethanoyl halide or butanoyl halide. Got it? Now suppose I say that it is not considered as a primary functional group. So there may be a chance that your given chain has carboxylic acid in it, and carboxylic acid has the highest priority. So in that case you have to use your acid halide as your secondary functional group or subsidiary functional group. So in that case you won't use the suffix ol halide because that would be already occupied by the oic acid. So what we will use? We will use halocarbonyl, HALOCARBONYL, halocarbonyl as the prefix. Next we have ester. Okay. So in ester, it's very simple. You will name it as alkyl alkanoate. How do we name it? For example, if we take CH3 COOCH3, so that would be an example of your ester. You will name it as methyl methanoate. Okay, is it clear to you? So remember the way to name it. Now next, what will happen if your ester is acting as a secondary functional group or a subsidiary functional group? In that case, what you will use as the prefix? You will use the prefix as alkyl carbonyl, alkoxy carbonyl. Okay, so for acid halide it is halocarbonyl, and for ester it is alkoxy carbonyl. Got it? Lastly, we have this nitrile, where a C triple bond N is attached to the main chain. In this case, you will use nitrile if your given functional group is acting as the primary functional group or the principal functional group. So it can be named as ethane nitrile, methane nitrile, or not the methane nitrile, ethane nitrile, butane nitrile, or propane nitrile. But suppose your nitrile is acting as the secondary or subsidiary functional group, then what you will do? You will use the prefix cyno. What you will use? You will use the prefix cyno to represent its presence as well as its position. So let me just summarize it for you. For alcohol, the suffix is ol, the prefix is hydroxy. Then for aldehyde, it is al and the prefix is formyl. For amine, the suffix is amine and the prefix is amino. Next, what we have? We have this ketone. So for ketone, the suffix is on and the prefix is oxo. For carboxylic acid, your suffix is oic acid and your prefix is carboxy. Then after, we have this amides. So for amides, the suffix is what? Amide and the prefix is your amido. Lastly, we have this acid halide, ester and nitrile. For acid halide, the suffix is oil halide and your prefix is halocarbonyl. For acid halide. For ester, your suffix is ovate and your prefix is alkoxy carbonyl, and for nitrile, your suffix is nitrile only and the prefix is cyno. So try to remember this. It's very, very important for doing the nomenclature of various compounds. I hope it is clear to you. Now moving on to the next part. It is classification of carbon and hydrogen atom. So it is based upon the connectivity of your carbon. To how many carbons your given carbon is attached, and also what is the degree of hydrogen. So both are important. Both are being classified. So talking about this, so when carbon atom is attached with only one other carbon atom, then it is named as primary carbo atom. So this will be further used in many contexts such as primary alcohol. Then we have our primary haloalkane, primary you can say amine. So all of them are used or applied with the help of this concept, which is says that if your carbon is attached to only one carbon atom, then we name it as primary carbon atom. After that, we have secondary carbon atom, in which the carbon atom is attached to two other carbon atom. Very simple. Then we have this tertiary carbon atom. It's very simple. It will be attached to three other carbon atom. So what can be the immediate example of that? You can take the example of secondary butyl. Okay. Moving on to the last one, which is known as quaternary carbon atom, in which your carbon atom is attached to four other carbon atom. So this is the classification of carbon. Now what about hydrogen? So moving on to the classification of hydrogen, if your hydrogen is attached to a 1 degree carbon atom, then it is named as 1 degree hydrogen or primary hydrogen. Moving on to the next, if your given hydrogen is attached to a secondary carbon, then we will call it as secondary hydrogen. It's very simple. So it's kind of predictable. So the hydrogen that is attached to a tertiary carbon means a carbon that is attached to three other carbon. We will call it as a 3-degree carbon. Now, a very important common terminology that is used often in your naming part and it can confuse you. And that is related to the trivial system of using alpha, beta and gamma. So they are similar to that of the naming part, but in place of 1, 2, 3, we use this alpha, beta, gamma and delta. So how do we do it? What about alpha carbon? So it is the carbon atom which is directly connected to the functional group. Okay. So we can take the example of CH3COOH, which is acetic acid. So here your carbon which is attached to three other hydrogens and one carboxylic group is a alpha carbon because it is just next to the functional group. Now, if we try to extend our chain and we write it as CH3CH2COOH means C2H5OH, then the terminal carbon which is present on the aryl side of your carboxylic acid, so that can be called as your beta carbon because it is present at the second position if you count it from the carbon that is next to carboxylic acid. Okay, so this is known as the beta carbon. And lastly, we can have gamma and delta also. Similarly, we have the hydrogens. So it is very simple. In the same context of your 1-degree hydrogen, if the hydrogen is attached to alpha carbon, we will name it as the alpha hydrogen. And there is a specific reaction regarding this same terminology named as alpha elimination and beta elimination. We will see that in the hydrocarbon chapter as well. So we can just simply say it as the hydrogen which is attached to the primary carbon is called the primary hydrogen and the hydrogen which is attached to the alpha carbon is called the alpha hydrogen. Then the hydrogen which will be attached to the beta carbon will be called as the beta hydrogen. So here is an example of the same. So there are three examples. In the first case, the functional group is taken as your chlorine. In the second case, it is taken as the carboxylic acid. And the third case, it is taken as the aldehyde. We have three compounds separated by commas. Next, we can say that here we are not starting from that carbon. If I talk about the carboxylic acid COOH, here we are not starting from the counting from that carbon, which is a part of functional group. We will start from the next adjacent carbon. So here you can see it very clearly that the CH2 group is given your alpha position, which is next to the carboxylic group. And then the CH3 group at the farther end of the carboxylic group is given as the beta position. Similarly, you can see the CHO group, which is attached to CH2, and that CH2 is given the alpha, and the next one is CH3, which is given the beta. Now we can conclude it same in the terms of those functional groups that have no carbon in that structure. So for that, we have taken the halogen, which is chlorine. So next to the chlorine, we have this CH2 group, and hence we are calling it as the alpha. And then we have this beta. So you should remember this way of representing the carbon's position, and it is very important in some reactions. For example, the whole definition of aldol reaction is in most cases based upon this alpha position. So we say that your carbonyl group, whether aldehyde or ketone, must have a alpha hydrogen to undergo aldol reaction, or else it will not give you your product. Okay, got it? So what can be the examples of those carbon which have no alpha hydrogen attached to it? So the quick example would be of your benzaldehyde. If you take the case of benzaldehyde, the formyl group, which is your CHO, it is attached to the benzene, means it is a part of the benzene ring, and there the carbon has the adjacent carbon to the carbonyl group has no hydrogen onto it or no alpha hydrogen onto it. Okay, so you can only understand that context when you will know this way of representing the hydrogen's position. Now moving on to the rules for naming a compound, which is our IUPAC system. So if you know all of this, now we can move into the real stuff. I will tell you the obvious steps. The first one is identifying the longest chain. So the one with the functional group is taken as the longest carbon chain, and then we start the numbering. What about numbering? So numbering is done from that carbon where the branching is nearest. Okay, means the number of the branch or the carbon number of the branch should be of lowest type. Got it? And it will always start from the terminal carbon. So it can be from the right hand side of the longest chain or from the left hand side of the longest chain. It depends upon the position of functional group. Then after, if a situation comes that two substituents are found at equivalent position, in that case, you will do the numbering in alphabetical order. So here the substituent means that you are talking about the alkyl groups. For example, if we take the methyl and ethyl, then ethyl will be given a greater priority as compared to the methyl, because ethyl starts with E and methyl starts with M. Remember, this substituent is something which is not related to functional group. It is related to the alkyl chains like your methyl, propyl, then propenyl. Now, how do we name the side chains? So it's very simple. You will only replace the AN part with the YL. Like methane is written as methyl, propane is written as propenyl, then your ethane is written as ethyl. As simple as that. You can just carry it forward. It can be butane as butyl, pentane as pentyl. I hope this makes sense. Now the same thing is applied to those names which are used in the common name system. For example, isobutane, if it is attached to a chain, then we name it as isobutyl or isopropyl or neopentyl. Then we can have secondary butyl. So these are some of the common names which are used as a part of a branch. Next, if there is a condition that two chains have the same size, then one with the greater number of side chains or the greater number of alkyl chains will be taken as the main or the parent or the skeletal chain. Okay. The next rule is about the longest chain. The number of the longest chain containing the functional group must start from the end that gives the functional group the lowest possible number. So this ensures a standardized and a consistent naming system for organic molecule. So this is something which is known as lowest locant rule. So what do we do? In case of polysubstituted main chain, we just add the position of the substituents. So suppose it is present at 2, 3, 4, we add them. And then we get a sum. Now there can be a second option also, since there are two terminal of the longer chain. So you will count it from the opposite side, and then again you will add the position of the substituents. Now here you have two sums. Okay. The one with the lowest value is considered as the proper chain, or the better way to name it, or the better numbering part, which is giving you the lowest sum. So this is known as the lowest sum rule. We will talk about them using illustrations. So here is the last point. In case of the polyfunctional organic compound, you have a single functional group that is designated as the principal functional group. And this is based upon priority rules, and the compound is named then accordingly. So let me just give you the priority order of the functional group. So the order of decreasing priority of some functional group are as follows. So this is the decreasing priority. We start from the carboxyl. So carboxyl is given the highest priority. Then we have this SO3H. Then we have ester. After that we have carbonyl. Then we have amide. And after that we have cyno, formyl, oxo, hydroxyl, amino, alkene, and alkyne. So this is the order of your priority in case the functional group is present in the main chain in multiple times and of multiple type as well. Okay. Now, if you are getting two functional group, you will give the lowest sum or the lowest number to the carboxyl. Then you will look for the SO3H, then for the ester. How can you remember it? It's very simple. First of all, you should remember that carboxyl is present at the start and triple bond at the end. Next, what you do, you keep on removing the parts from it. If you remove hydrogen, you will get R. Then, keeping this O constant, we will again remove one more OR. So we will first remove this H, we will get R. We will remove this OR, we will get Cl. Then Cl is replaced with NH2. Okay, so this is quite clear. Next, we have this carbonyl. So we are one more time changing the position. So basically we are moving from a oxidized carbon to a reduced carbon. So this is the most reduced carbon. Got it? I hope it is clear to you. So remember this order, it is very important to decide the principal functional group in case there is a case of polyfunctionality. Next, here are some examples. So we'll talk about this example with the help of the rules that we have learned just now. So first one, in this given chain, there are two possibilities. One is that we can start from the rare carbon, which is this one, 1, 2, 3, 4, 5, 6. Or we can start from this carbon, where the OH group is attached. So which one we will choose? As I said earlier, you will always choose that short chain or the long chain which has the maximum number of functional group. Therefore, we have started from this carbon rather than this one, although the longest chain is of 6 length possible. Got it? So we start from the right hand side and we move linearly onto the left hand side. In this chronology, we are getting hydroxyl group attached to two positions, at the first position and then at the fourth position. What about the substituent? So the substituent is your ethyl. Now the question comes, how are we putting it? What is the way to put it? Okay, so it's very simple. First of all, what you will do is you will put the substituent's name, then the root name, then after we will place the next suffix which is deciding your saturation, whether it is unsaturated or saturated. So here it is clearly saturated, so we'll use AN. And lastly, we will name the primary functional group. Okay, so this is the way to name a complete organic compound. So here we will consider that chain which has the maximum number of functional group inside it, no matter whatever longer chain can be possible. Okay, moving on to the next example, we have this 4-keto pentanoic acid. So here we have used the term keto. You can also use oxo instead of it. There is no issue in using that. Now the question arises, why are we starting the numbering from the right hand side? So the obvious reason is that your carboxylic acid has a higher priority. We have seen it in the start that the carboxylic is given the higher priority. Therefore, we have started it from the right hand side. Now in that chronology, we see that the oxo group or your keto group is present at the fourth position. So first of all, we will give it to the prefix. So 4-keto will act as the prefix. Then the root name, which is decided from the number of the carbon in the main skeletal chain. So it is 5. Therefore, we will use the term pent. Lastly, we will use the suffix for the primary functional group. So the suffix for the primary functional group, which is a carboxylic acid, is oic acid, and hence we are getting the name 4-ketopentoic acid or 4-oxopentoic acid. Okay, I hope this is clear to you. Next question. So here is an example of cyclic compound. So we have dealt with 2 acyclic compound. Now we'll see onto the cyclic compound. Here, what we are saying that we are using a prefix which is cyclo. Okay, what we are using cyclo here, and it is always used when your given compound is cyclic in nature to represent that we are not having a linear chain. So we have written it as cyclobutane. Then we have carboxylic acid. Okay, is it clear to you? You can also write it as cyclobutanoic acid, or you can write it as cyclobutane carboxylic acid. Both are good to go. So here, the carbon containing functional group is not considered the cyclic ring. Okay, therefore we are not writing it as cyclobutanoic acid because the carboxylic acid is not the part of the main chain. We are writing it separately. I hope this makes sense to you. So the statement is that if your carboxylic group is not attached to the main chain, which we are considering for the naming, then we will simply add it as the carboxylic acid. But still, it is given the highest priority because no other group is present, and if it was present also, then in that case your carboxylic acid has the highest priority. The cyclobutane carboxylic acid is the final name of the given compound. Moving on to the next one. So anyone who has a doubt till this part, you can ask it here in the comment section. So here is the next one. This is an example of aliphatic and aromatic ring joined together. Now if I ask you, in which classification would you put this compound? Without any hesitation, you will always say that since your compound is containing a ring, so first of all it will go to the group of cyclic compound. Then after, your members of the ring, means the elements of the ring are all carbon, therefore it will go under the homocyclic. Next question, whether it will be a aromatic or a non-aromatic, since it is containing a benzene, so of course it will be aromatic and a benzenoid aromatic compound. Okay, so this will come under the classification of benzenoid aromatic compound. So our task was to assign name to it. How you will do it? It's very simple. First of all, you will take that chain that includes your primary functional group, and that will be of course your carboxylic acid. So here we've started with this chain. So 1, 2, 3, 4. Okay, we can't name it down to this ring. It is not possible to name it separately. So we have to go along with the aliphatic chain. Next question arises, what is the prefix that is used for this benzene ring? As long as this benzene ring is directly attached to the main functional group, we call it as a phenyl. But if there is a carbon in between the primary functional group and your main or the longest carbon chain, we name it as benzyl. So there are two cases. One is of benzyl and the second one is of phenyl. So what did I say? So in this case, your phenyl group is or your benzene is directly attached to the main chain. So we are using the prefix phenyl. But suppose between this carbon number 2 and the phenyl group, we have a carbon in middle. Then in that case, your whole group along with that middle carbon, the phenyl will be turned to benzyl. Okay. So this is very important to remember. We have the example of it also. We have benzyl alcohol. So if we have a benzene ring, then we have a CH2 group and a OH group attached to it. We call it as benzyl alcohol. Okay. But if it is not the case and your OH group is directly attached to the benzene ring, we name it as phenol. Okay. Now in this case, we know that why we are choosing the aliphatic chain, because the functional group is not that directly attached to the benzene ring. So the ring is considered as your branching part and it is named using the term phenyl. Okay. So this was all about the theory part. So just wait for a while. I will just open the question. Meanwhile, if you have a doubt, you can ask it right now in the comment section. So today we will do question number 8 to 14. Yesterday we have started from 1 and moved on to 7. So rest of the questions will be covered today. Now most of the questions will be coming from the isomer part and your nomenclature part that we have studied right now. There will be total of 7 questions starting from the first one. Question number 8, in which it is asked that out of the following cases, the functional group isomerism is not possible in which of the case? So functional group isomerism means that compounds have the same molecular formula but different functional groups are present in them. So in which case it is not possible? The options are alcohols, aldehydes, alkyl halides and your cyanides. How you will do it? So remember, you can interconvert one functional group to the other functional group by not changing the formula and only changing the structure of the functional group. Okay. So if I start from the alcohol, you can move your oxygen between the carbon and hydrogen onto between the two carbons. Similarly, you can move your oxygen of carbonyl from the terminal part to the middle part to make it a ketone. Okay. In this way, one functional group can be converted to another. So I'm not talking about the real conversion or the chemical conversion. Here I'm talking about the form for conversion with the help of your pen. Okay, normal. We are just changing the structure by writing it in a different way. Okay, there is no real conversion going on. But we cannot say the same about alkyl halides because alkyl halide is a functional group having only one atom and that is also monovalent in nature. So it cannot change its structure at all. And last one is cyanide. So cyanide is something which can show functional group isomerism. So you can just give your answer in the comment section. I will wait for 2 minutes. Then we'll move on to the correct answer. Remember, what are functional group isomers? The two isomers which have the same molecular formula but different functional group. Okay. It's a direct theoretical question. Just quickly give the answer in the comment section. And also tell me if you know that what are the corresponding functional groups that are possible to transform your alcohol into a different one, aldehyde into a different one, and cyanide and alkyl halide into a different one if they are not the answers. Okay, so moving on to the correct answer. So here we have answer as C. Yes, hopefully the correct answer is option C. So it's very simple. I said it earlier that alkyl halides are not capable of showing the functional group isomers. So for aldehyde, we have the corresponding functional group as the ketone. Then the next one is your alkoxy hydroxy, which is capable of converting it into ether. And what is the last one? We have the cyanide. Okay. So what is the possible functional group, the isomers that can be formed from the cyanides? Can you tell me? So I said that what is the possible functional group conversion that your cyanide can undergo without changing the molecular formula? So if you know it, just write into the comment section. Okay, the correct answer will be isocyanide. So the case of your cyanide is basically the connection of your CN group attached to the carbon to the main carbon chain or to the other carbon chain. If you want to convert it into isocyanide, you just have to revert the connection. So here, in this case, the CN group will be attached from the nitrogen side and not from the carbon side. So that would result in isocyanide. It's very simple. It's N triple bond C and N is attached to a different one. Okay. I hope this is clear to you. Now moving on to the next one. Question number 9. we have to identify the compound that exhibits tautomerism. So tautomerism can be of two types: 1,2 migration and 1,3 migration. The most famous is 1,3 migration in tautomerism, that is known as keto-enol tautomerism. So basically, your keto form, which is C double bond O, is changed to the enol form. Okay, means a doubly bonded carbon attached to a OH. So rather than keeping it attached doubly bonded to the oxygen, we keep it attached to a OH group, and this interconversion is seen chemically. So if you take a ketone, then in a equilibrium there is a possibility that your keto can go into the enol form through the tautomerism. Okay, but the percentage of your enol form is always minor in most of the cases. So there are some exceptions to it. Due to hydrogen bonding and all, we can obviously see some ketones which are predominantly existing in the enol form. But most of the keto forms are stable, and the reason is that your keto form is stable due to the carbon doubly bonded to the oxygen. Okay, so the carbon which is double bonded to the oxygen is considered to be highly stable as compared to carbon attached through single bond to the oxygen. Okay, so that is the reason your keto one is, or the keto form is, highly stable. Now here you have to see, out of the given options, 2-butene, lactic acid, 2-pentanone and ethane, which compound is capable of exhibiting tautomerism, means the conversion of one functional group to the other through proton transfer. And remember, this transformation is something which is seen in the dynamic equilibrium in most of the cases. Okay, in a single molecule. So just try to find out the answer by writing the structure and then comment your answer in the comment section. Your time starts now. So let us move on to the correct answer. It will be option C, which is 2-pentanone. Now how it is correct? It's very simple. First of all, let us see the definition. So tautomerism is the phenomena where two isomeric forms which have different functional groups spontaneously interconvert into each other. The term tautomer refers to constitutional isomers that undergo this rapid interconversions, making it possible to isolate them independently. So the isolation is the most important part. Now, as I said earlier, the pentanone is the correct answer. So I've taken a fragment of pentanone here and shown how that keto-enol tautomerism is taking place. It is clearly a case of chemical equilibrium between two interconvertible structures, a ketone form and an enol form. These two forms are structural isomer that readily interconvert by the relocation of hydrogen atom and a change in the position of pi bond. So you can see here that this pi bond is going on to the oxygen and the adjacent hydrogen is transferred onto the negative charged oxygen. But at the same time, the sigma bond between the carbon and hydrogen is meant to formed between the two carbons, and hence we are getting a enol form. Now remember the structure of enol form, how does it looks? So we have now two carbon attached through double bond and a OH group attached to the same carbon which was previously a carbonyl carbon. So this one is the keto form and this one is right side is the enol form. Now how the keto form is more stable? You can clearly see that in the keto form the carbon is attached to oxygen through a double bond, which is a very stable condition for a carbon bonded to oxygen. Whereas in the case of enol form, your carbon and oxygen have a single bond and they are very less stable as compared to this keto form. So therefore your keto form is stable is in most of the cases. Hence we can say that the 2-pentane exhibit the tautomerism. Next question. You have to tell in the question number 10, for a compound whose molecular formula is given, what will be the number of possible stereoisomers. Now, if you are considering stereoisomers, then first you will have to find the chiral center in it. The number of chiral centers will determine the formula you apply, which is 2 to the power n. Here n is the number of chiral center in that particular molecule. With the help of this formula, we can directly tell how many stereoisomers are possible in the molecule or this compound. A very interesting question is presented: CH3, CH double bond, CH, then single bond CH, then OH. Options are, and then methyl, that is CH3. Options are 3, 2, 4 or 6. So you have to choose one of them. Your time starts now. It's a very simple one. Just count the number of chiral centers. The one carbon that contains 4 different kind of groups. If you get the answer, just write it in the comment section. What you have to do, you have to count the number of chiral center. Now one more possibility is there, that is of finding a geometrical isomer. So under stereoisomer, we have two kinds of isomerism: optical isomerism and geometrical isomerism. So optical isomerism comes from the chiral carbon, which is a carbon attached to 4 different groups. And geometrical isomerism comes from cis trans configuration. Okay. So that is predominantly in your standard is due to the double bond. Right. So we have a double bond here. Therefore, you should consider both the stereo centers. And then just take the number of stereo center as the power of 2 and you will get your number of possible stereoisomers for the given compound. So what will be your answer? Can you tell me in the comment section? Okay. So moving on to the correct answer, it will be 4, which is option C. How you will do it? So for the given compound CH3 single bond CH double bond CH single bond CH OH CH3, the total number of isomers are 4. How we are saying it? Because there are two stereogenic centers that are capable of creating stereoisomers. What are those centers? The first one is the double bond. Here we have a double bond, and the second one is the carbon which is attached to the hydroxyl group. So it is attached to 4 different groups. One is hydroxyl, second one is hydrogen, third one is this methyl, and last one is this large alkyl group along with the double bond. So the carbon containing the hydroxy group is a chiral carbon because of the 4 different groups. Now we have 2 stereogenic center. One is the double bond and one is the chiral center. Hence, how do we calculate the total number of stereoisomers? It's very simple. We take this number of stereo centers as the power of 2. So 2 raised to the power 2. That will give you 2 square, and hence 4 will be your answer. Now why are we telling it? How those isomers are possible? First of all, you will take this double bond having the configuration as cis. So one will be cis and one will be trans. Similarly, for this chiral center, 2 stereo are possible. One is R configuration and second one is S configuration. Now the process starts. First of all, you will take the cis part, and with that you will take R and S both. So cis R and cis with S configuration. So 2 of them are possible in this way. The other way is to take the trans one and then again repeat that same thing of taking R and S. So cis, then R configuration, cis and then S configuration. Similarly, trans and then R configuration, and trans and then the S configuration. So for each stereo center we have 2 isomers possible. Got it? And that is giving you the formula of 2n, which is giving you the answer as your 4. Next question. Question number 11. Question says that 3-methyl pent-2-ene on reaction with HBr in the presence of peroxide forms an addition product. We have to find out the number of possible stereoisomers for the product. Options are A 6, B 0, C 2 and D 4. Remember, what is the effect of peroxide here? So first you try it by yourself, then I will give you some hint to solve it. Okay, just try it by yourself. Okay, so coming back to the hint, since we are using a peroxide and the halide that is included is your bromine, always remember that this crash effect or your anti-Markovnikov product is only possible during the addition of your HBr to alkene when we are using Br as the halide and your benzoyl peroxide as the catalyst. Got it? So whenever you do such reaction, then your product is reversed. Means in the normal condition, what you will see that your negative addendum. So since we are adding here HBr, the negative addendum would be Br. So Br will be attached to that carbon which is forming the stable carbocation. But in the case of benzoyl peroxide, the thing is reversed. The bromine is attached to that carbon which is forming the least carbocation. Okay. Now, according to that, we have to first write the product and then we have to count the number of stereoisomers that are possible with that given product. The correct answer would be D, which is 4. How we'll do it? The formula 2n is used to determine the maximum possible number of stereoisomers for the molecule with n chiral centers. Here also, so chiral center means asymmetric carbon atoms, provided the molecule is chiral overall and does not possess any internal plane of symmetry or center of inversion. So this must be always in your mind. If it is bisected into two halves, then this formula is not validated. But as long as your given compound is not symmetrical, then in that case you will simply use this 2n formula. The reaction describes an anti-Markovnikov's addition of HBr to an alkene due to the presence of peroxide. The starting material 3-methyl pent-2-ene. The product formed will be 2-bromomethyl 3-methyl pentane. So this is your structure. Now, if you see here in the structure, then we have at the second position bromine attached to it because this second carbon is forming the least stable carbocation as it is a secondary carbon. Always remember, secondary carbocation are less stable, and the reason behind it is that it is not stabilized by the plus I effect, okay, and the hyperconjugation effect. Therefore, your carbocation will be more stable on the third carbon and not on the second one. Then, as I said earlier, in the case of peroxide, your bromine will go to that carbon which has a less carbocation or has a probability of forming the less stable carbocation. Got it? So bromine gets attached to this point. Now the question arises, how many stereo centers are possible? Then only we will be able to find the number of possible stereoisomers. Okay? So from that way, you can easily calculate your answer. Next, question number 12. So in this question, which of the following compound will exhibit geometrical isomerism? 1-phenyl, 2-butene, then 3-phenyl, 1-butene, 2-phenyl, 1-butene, or 1,1-diphenyl, 1-propane. How you will do it? So first of all, you will see that whether your given compound has same substituents across the double bond or not. If it is not the case, your compound will exhibit geometrical isomer, which is your cis and trans. So just try to draw the structure of the compound with the given formula and see whether there is a possibility of different groups or not. So if you get the answer, write it in the comment section. I will give you 1 to 2 minutes. It's a very simple question. As soon as you draw the structure, you will get your answer quickly. Remember, your carbon must not contain similar group or else it will not show geometrical isomerism. How you will draw the structure? For the first one, you will take a 4-carbon chain. On the second position, you will take a double bond, and the first position you will paste a phenyl group. Similarly, for the B option, you will take a 4-carbon chain with double bond at the first carbon and phenyl group at the third carbon. For the option number C, you will again draw a 4-member chain, aliphatic chain, and then you will place double bond at the first position and phenyl at the second position. And lastly, you will take a 3-member chain, which is a propane, and at the first position you will place 2 phenylic groups. Of course, this last one is not capable of showing geometrical isomer because it has no double bond or a ring which can have two different possibilities. So there comes a new thing, which is a ring showing geometrical isomerism. Suppose you have a ring and you are seeing that on that ring we have two substituents. Both of them are methyl. Okay. If both of the methyl are pointing upwards, suppose you place your compound in the table, on the table like this, your ring compound, and both of the OH group are pointing upward direction or in the same direction, I would say. So that would be the case of cis, and if they are pointing in the opposite direction, that would be the case of trans. So in this way, your cyclic compounds are also capable of showing geometrical isomerism without the help of or without the aid of double bond. So moving on to with this, the correct answer would be A, 1-phenyl 2-butene. Why it is the correct answer? So you should remember the rule, alkenes in which different functional groups are attached across the double bond, they are capable of showing the geometrical isomers. So if that is the case, then what will be the answer? Your answer would be 1-phenyl 2-butene. So let us draw the structure. So this is your trans 1-phenyl 2-butene and cis 1-phenyl 2-butene. Here on the first position we have the phenyl group, on the second we have the double bond. Now you can place the groups on the same side and then on the opposite side. In the first case, we have taken hydrogens on the opposite side or on diagonal positions, right? So that is creating a trans 1-phenyl 2-butene. In the next part, what we are doing, we are taking both hydrogens on the same side or on the adjacent side. So that would create a cis configuration. So we are getting the compound as cis 1-phenyl 2-butene. Okay, see here, it's very clear that the two hydrogens are present on the same side, and the first case they are present on the diagonal side. Therefore, your 1-phenyl 2-butene is capable of showing cis trans configuration. Okay. Now moving on further, we can look upon other compounds also. In case of your 3-phenyl 1-butene, we have same groups which are present on the carbon. So you can see here that the two encircled atoms are hydrogens itself. You can change the position of the both of the hydrogen, you will get the same result. As the result of that, you won't see a case of geometrical isomers. Okay, so remember that it's very important. If your doubly bonded carbon has two different substituents, both of the doubly bonded carbon have two different substituents, then and then only it will show geometrical isomers, or else it would not exhibit geometrical isomerism. Next question. If I take here 2-phenyl 1-butene, here also you will notice that upon drawing the structure, same groups are present on the same carbon. As a result of this, it is not showing geometrical isomer. See here, the two hydrogens are again present on the same carbon, right, on the doubly bonded carbon. Hence, it will not show geometrical isomers. A question is here for you, that how can we change the geometrical isomer from one form to another, that is from cis to trans. If it is possible of showing the cis trans configuration, how can we interconvert it? So the answer would be, there is only one way to do it, and that is of breaking the bond. Meaning that your rotation along double bond is not allowed, or along triple bond is even not allowed. But you can rotate two carbons along the single bond. That is something which is possible. So we have talked about this in the previous class also, right? Lastly, we have 1,1-diphenyl 1-propane. As I said it in the start, that it is a saturated compound and not a cyclic one at the same time. Hence, neither it can show geometrical isomerism or it cannot show any isomeric like your optical one or any stereoisomeric. I hope this is clear to you. Next question. Which of the following compound can show metamerism? Now, metamerism is what? If we have the single atom in the between or a single species in the between, and then we are exchanging positions on the either side. Okay, and we are getting two different kinds of functionality, then in that case, your compound is capable of showing metamerism. Your options are given here. First one is HC double bond OCH3. Second one C2H5 SC2H5. Third one CH3OCH3, and last one CH3OC2H5. The first one is obviously not possible. You won't change the position of hydrogen and CH3. It is not possible at all. It will give the same thing, okay? It will give you a different functional group. Therefore, it will not show metamerism. Remember, the functional group, the functionality should not change. If you place CH3 here and H in place of CH3, what you will get? You will get a acetic acid, which is not here the case. Now, the next one is sulfur attached to two different groups. One is C2H5 and the other one is C2H5. So, can you change the alkyl groups? Yes. You can bring one carbon from the right hand side onto the left hand side, and that will give you C3H8, whereas on the right hand side you will be left with the CH3. Hence, we are seeing the change of alkyl groups across a functional group. Therefore, it is an example of metamerism. Yes, the correct answer would be B. Next option, we have CH3OCH3. Here you can obviously interchange the alkyl group, but you will get the same result. And since there is one carbon, which is the minimum count, hence you cannot move carbon from one side onto another. So both of them are not possible. Lastly, CH3OC2H5. In this case also, if you move a carbon from the C2H5 onto the CH3 side, you will get that same starting part. And there will be no form of any or no trace of any metamerism. Therefore, your correct answer will be C2H5S C2H5. So, metamerism is possible in ethers, thioethers. So, what are thioethers? In which we have sulfur rather than oxygen. So, we name it as thioethers. So, there are some, I would say, generic terms which are used in most of the cases. Like if we place sulfur in place of nitrogen, oxygen, we'll name it as thio. Right? Like we have thionic acid. Second, if we place nitrogen in place of carbon, then we name it as iso. Like we have isocyanide in place of cyanide. Got it? Similarly, cyano in place of isocyano. Then the next part is the secondary amine. So if you change the functional group across a nitrogen, then you will get two types of Two types of compound. Okay. And lastly, we have esters. In the case of ester, you can also change the position, but in the first option, the ester change of position would result in a carboxylic acid, and that is something which is not acceptable for metamerism. Remember, the metamers belong to the same family but different in the nature of the alkyl group, and if you change the alkyl group in case of the first option, you will change your ester to your carboxylic acid, right? Hence, your C2H5 SC2H5 is capable of showing metamerism. Our last question of today's class. Nitroethane can exhibit one of the following kind of isomerism. First one is metamerism, second one is optical activity, third one is tautomerism, and the fourth one is position isomerism. Now let me tell you about each of them one by one. As I said it in the start only, we'll talk about the isomerism part in the question. So what are metamers? We have studied a lot about this in the previous question. In the case where your alkyl groups are changed across a given functional group without changing the functionality of that group, in that case we name it as metamerism. Okay. Next, optical activity. So for optical activity, your mirror image should not superimpose onto the original image. And how do we do it without using the mirror? Obviously we can't use it. The way to do is to see the plane of symmetry or the point of inversion. So if there is a plane of symmetry that divides your given molecule into two equal halves, then in that case you will name your compound as optically inactive, or else you will call it as optically active. Then after we have C as tautomerism. So what was tautomerism? In this case, your hydrogen or your proton is changing its position via reversible reaction or a reversible dynamic equilibrium. The classic example of it would be the ketone converting into the enol, the keto-eno tautomerism. Okay. Last one is position isomerism. What is position isomerism? Where the position of functional group is changing. Suppose we have a pentane ring and chlorine is attached to the first carbon. Suppose if you change the position of your chlorine to the second carbon, right, then onto the third carbon. So we are getting different compound, but the formula will remain same, and it is happening due to the different position of your functional group on the skeletal chain. Hence, you will name it as position isomerism. If I try to divide the whole tree, so we have two kinds of isomerism. One is stereo, second one is structural. In stereo, we have this geometrical and your optical. Geometrical means cis, trans and all, and optical means RS configuration. Then, apart from stereo, we have this structural isomer. Under structural isomer, we have various possibilities. First, we have position, where the position of the functional group would change. Second, we have this chain isomer, where the length of the chain would change continuously. Okay. Then we also name it as ring chain isomerism. Got it? Then we have tautomerism and we have metamerism. So this is your whole tree of your isomerism part. Got it? Now moving on to the answer of this question 14, we have to tell that whether your nitroethane will exhibit which kind of isomerism. The correct answer is tautomerism. Now first try to remember what was the structure of nitroethane. We said that nitro stands for NO2, and since we are naming it as nitroethane, therefore an NO2 group will be attached to a ethane, which is C2H5. So the overall formula will be C2H5NO2. Next, how does nitroethane exhibit tautomerism? It's very simple. So this is the structure of nitromethane. Now what are we doing here? Initially, we have our nitrogen bonded to oxygen through a double bond. Next, what are we doing here? We are transferring this pi bond between the nitrogen and oxygen onto the carbon and nitrogen. But the position of the charge is remaining same. One is on the oxygen, which is singly bonded to nitrogen, and one is on the nitrogen, which is in the middle, which is a positive charge. During the moving or removal of this pi bond between nitrogen and oxygen and acceptance to it to the between the carbon and nitrogen, we are disturbing the valency of the oxygen in nitroethane. So what do? We complete its valency by taking one hydrogen from the alpha carbon, which is your next carbon onto the functional group, and putting onto the oxygen whose valency is not completed. As a result of this, we are getting a new structure out of this nitroethane, which is the tautomer of the nitroethane. Okay. So the correct answer would be C in this way. Now I would ask you a example in which the enol form is highly stable as compared to the ketone form. So this is a very famous question. Often tautomerism is related to that part because in most of the cases the keto form is considered to be less stable, more stable. But in specific cases, out of which I will tell you one, you will see that there is a stability of the enol form. So first you can name it, or either I will tell you the name and try to draw the whole structure and see that why is it more stable. I will tell you about in detail in the next class. Just write if you know it. I am giving you some time to write it, or else I will tell you the name. Okay. So the answer to that question is pent acetyl acetone. Yes, you have told it correctly. The correct answer is acetyl acetone. So this acetyl acetone has most of its configuration stable in the enol form. And the reason behind it is what? Can you tell me what is the reason behind it? Why is the enol form more stable? For the specific reason for it, you can just try to draw the enol form and see that how that hydrogen is stabilized. or why the seed single bond O is stabilized. Okay, so let's see, since we are lacking time, so I will tell you directly. The reason is that your hydrogen, which you get upon doing the tautomerism, it is now hydrogen bonded to the doubly bonded oxygen. Okay, so in case of your acetyl acetone, we have two carbons containing double bond O, and in between that we have one carbon. In overall, we get a 5-membered ring, and the interaction that we are seeing is due to the hydrogen bonding between the hydrogen of oxygen and the oxygen of the doubly bonded carbon. So just try to figure out the name once more if you want. So the name is already in the chat, right? Or else you can find it by yourself. It is acetyl acetone. Thank you for joining the session. I hope you enjoyed it.
Hello everyone. So welcome to today class. In today lecture, we are going to discuss Cartesian system of rectangular coordinate. Okay. So at first, let's analyze this chapter for the JEE Mains examination. So as this chapter come to the under the topic straight line. So according to last 5 year, the chapter weight is for this chapter is 3.83%. Okay. And in the year 2024, one question came from the topic angle between the line, that is given by the formula tan theta is equal to m2 minus m1 by 1 plus m1 into m2, and this is a topic of straight line. Okay. In 2023, one question from the topic area of triangle, then two question in the year 2022 based on area of quadrilateral orthocenter of a triangle. Okay. Then in the year 2021, again one question from the topic area of triangle. In 2020, one question from the topic centroid of triangle, that is given by x1 plus x2 plus x3 by 3, comma y1 plus y2 plus y3 by 3. And in the 2019, one question from the topic slope of line. Okay. So in today's lecture, at first we will discuss what is rectangular coordinates. Okay. Like we know there is a x-axis then and y-axis, and how we represent a point on this system. What is Cartesian system? Okay. Then we will understand the distance formula. So if there is 2 points on the Cartesian system, then how we can calculate the distance. Okay. Then next is section formula, which explain how a point divide the line segment joining 2 points in a certain ratio. Okay. After that, we will know the formula how to calculate area of a triangle by using coordinate points. Okay. So if there is given a triangle and we know the vertices, coordinate of vertices, then how we can calculate area of triangle by using the coordinate points of the vertices. Okay. And next, area of some geometrical figure, and then coordinate of different points of triangle such as centroid. Okay. And then some important result. Next, we will study about change of axis. That's how we can shift the origin, how we can rotate our axis. Okay. After that, we will understand what is slope of a line, which determine the steepness of a line. Okay. Parallel and perpendicular lines on the coordinate axis. And finally, at the last, we will understand locus and its equation. Okay. So let's start. So at first we will discuss rectangular coordinates. So let x o x dash and y o y dash be a perpendicular axis in the plane. So there are two axes and both are perpendicular to each other, x axis and y axis, and this both axes intersect at a point O, and that is origin, as in the figure. Okay. Let P be any point on this plane. So how we can locate this plane? Okay. And that location is given by tuple ordered pair, that is coordinate of that point P, that is the location of point P according to this Cartesian system. Okay. So that is given by x comma y, where x represent the distance of point P along the x axis and y represent the distance of point P along the y axis. Okay. We draw PM perpendicular to OX, and that distance PM, that is equal to y, and this distance OM is x. So we can locate the point P by x and y. So this ordered pair x comma y is the location of point P x comma y in the Cartesian system. Okay. So this is your rectangular coordinate. Clear? Next, distance formula. So let we have 2 point on the Cartesian system. First point is P, that is x1 comma y1, and second one is Q, that is x2 comma y2. Then the distance of this points P from to Q is given by this formula PQ. Let's suppose the distance is D. So PQ is equal to D, that is root under x2 minus x1 whole square plus y2 minus y1 whole square. Or we can also write it as root under x1 minus x2 whole square plus y1 minus y2 whole square. So this is the formula to calculate distance of point P to Q. That is distance PQ, that we denote as D. Okay. And let's suppose one point is fixed, that is origin 0 comma 0, and another point, let's say x comma y. Then distance is given by root under x square plus y square, and this formula is coming from the above one. If we put x1 y1 as 0 comma 0 and x2 y2 as x comma y, then we get PQ is equal to root under x minus 0 square plus y minus 0 square, that is root under x square plus y square. Okay. Next, section formula. So let assume we have 2 points P x1 y1 and Q x2 y2 in the Cartesian system. Okay. And we join these 2 points. Then what is the coordinate of a point which divide this line segment in the ratio m is to m1 is to m2? Okay. So we have 2 point P and Q, and there is a point between this line segment which divide this line segment in the ratio of m1 is to m2. Then what is the coordinate of that point? And that coordinate is given by the section formula. Okay. And that is m1 x2 plus m2 x1 by m1 plus m2, m1 y2 plus m2 y1 by m1 plus m2. This is an internal division, that is a point between the line. Okay. And m1 m2 is the ratio. Okay. And when it intersect externally, then external section section formula is given by, that external division is given by m1 x2 minus m2 x1 by m1 minus m2 and m1 y2 minus m2 y1 by m1 minus m2. Okay. So this is the coordinate of point which divide the line segment externally in the ratio m1 is to m2. Okay. The first formula is for internally and second formula is for externally division. Okay. And let's suppose the point divide the line segment in the midpoint. Okay. That is, the point is the midpoint. So it divide equally. So that point is given by, let's suppose the line joining x1 y1 and x2 y2. So the midpoint is given by x1 plus x2 by 2, y1 plus y2 by 2. Okay. This formula can be easily derived by the formula of section formula. Next, coordinate of any point on one line segment which divide the line segment joining 2 point P x1 y1 and Q x2 y2 in the ratio lambda is to 1 are given by this formula x1 plus lambda x2 by lambda plus 1, y1 plus lambda y2 by lambda plus 1, and lambda is not equal to minus 1. So coordinate of the point when the line segment is divided in the ratio lambda is to 1 is given by this formula. Okay. Okay, next topic is area of a triangle. Okay, so let's suppose we have a triangle ABC. ABC are the vertices of triangle, and this coordinate of these vertices are x1 y1, x2 y2 and x3 y3. as shown in the figure. So the area of this triangle is given by this formula. That is, area of triangle ABC is 1 by 2 mod x1 by 2 plus x2 by 2 plus x3 y1 minus y1 x2 plus y2 x3 plus y3 x1. And when we rearrange this, we get 1 by 2 mod x1 y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. We just rearrange the above formula. We get this, that is area of a triangle ABC, when we know the vertices of the triangle. Okay. And we can also write this formula in the form of determinant. So 1 by 2 determinant of x1 y1 1, x2 y2 1, x3 y3 1. And when we expand this determinant, that is, we find this determinant by expanding along any row, along any first row. When we expand along first row, we get similar x1 y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. So we can write the formula in two form. First one is 1 by 2 mod x1 y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2, and also in the form of determinant, that is 1 by 2 determinant of x1 y1 1, x2 y2 1, x3 y3 1. The first row represent the first coordinate of a vertex A, that is x1 y1 and 1, and second row, that is x2 y2 second vertex, and the third row x3 y3 is third vertex. Okay. One important thing, area is always a positive quantity. Okay, so we take the mod sign, and its unit is square of unit of length. Okay, so two important thing, area is a positive quantity and its units is square unit. Okay. In the inverse problem, so what is the inverse problem? Let's suppose we are given area of triangle. Okay, and like that is given as a square unit. Then how we can write this formula? We write it as area of triangle, that is a square unit. So we write 1 by 2 mod x1 y1 1, x2 y2 1, x3 y3 1 is equal to a. Okay, that is 1 by 2 determinant x1 y1 1, x2 y2 1, x3 y3 1 is equal to plus minus a, because area is always positive quantity. So if we get a negative, then we take the mod sign. So a must be positive and negative during the calculation. So when we take a inverse problem, we take the both, we calculate for the both, one for plus and one for negative. Okay. And one application of area of triangle is that by using this formula, we can also check is the given points are collinear or not. Okay, so if A, B, C are given point and we know the coordinate of that points, so if you find the area of triangle made by this 3 point, that is, let's suppose area of triangle ABC, and that is 0, then it imply that the points are collinear. That is, area triangle made by them is, as area is 0, so the points must be collinear. That is, they are on the same line. Okay. Next is area of some geometrical figure. So suppose A and B are the adjacent side of a parallelogram. Okay, so we have a parallelogram A, B, C and D, and A and B are the adjacent side of this parallelogram, and theta is the angle between them. That is, theta is the angle between AD and AB. So AD and AB are the adjacent side, and the length of AB is A and length of AD is B, and the angle between them is theta. Then the area of parallelogram is given by the formula AB sine theta. Okay, simple. And area of convex quadrilateral with vertices x1 y1, x2 y2, x3 y3, x4 y4. So now we have vertex of convex quadrilateral. Then its area is given by 1 by 2 determinant x1 minus x3, y1 minus y3, x2 minus x4, y2 minus y4. Clear? Now, if a triangle, the vertex is given in this form, so if the triangle has vertices as a21 square 2a21, a22 square 2a2, and a third vertex is at3 square 2a3, then area of triangle is given by, so if the vertices is given in this form, then the area of triangle is given by a square t1 minus t2, t2 minus t3, t3 minus t1. Okay, so that's how we can calculate area of a parallelogram, area of convex collateral by using determinant, and area of a triangle when vertices are given in this way. Then area of triangle is given by this formula, a square t1 minus t2, t2 minus t3, and t3 minus t1. Okay, fourth, so area of triangle formed by coordinate axis and the line ax plus by plus c. So now this area is formed by coordinate axis, that is x axis and y axis, and the line ax plus by plus c. Okay, then that is given by c square by 2ab. So that's how we can calculate area of geometrical figure. Okay, some particular cases. Okay, so now we'll discuss different points of a triangle. So the first one is centroid. So what is centroid? Write the definition in comment section. What is centroid? Okay, anyone? So now we'll discuss different points of a triangle. So first one is centroid. So centroid is a some specific points of a triangle. So how we can define centroid? So the centroid of a triangle is the point of intersection of its median. It divides the median in the ratio 2:1. So as in this figure, we have a triangle with vertices A, B and C. The vertex A coordinate is x1, y1, and the vertex B x2, y2, and vertex C x3, y3. So centroid of a triangle is the point. So it's nothing but it is a point. And what is the definition of that point? So to define that particular point, that point is a intersection of its median. So we draw median through each vertex from vertex A to vertex BC to the opposite side, and according to the definition of median, it bisect the side BC. So and next we draw the median from the vertex V to its opposite side AC. So it bisect its opposite side AC, and the median from vertex C, it bisect the side AB. So when we draw this median, so the point where this median are intersecting, that point is centroid. Clear? Understand? So the black dotted point is centroid of this triangle. Okay. Now what is the property? The first property is for the centroid, it divides the median in the ratio 2:1. So this point, that the point centroid point, divide this median in the ratio of 2:1. And if A x1 y1, B x2 y2, C x3 y3 are the vertices of triangle ABC, then the coordinate of its centroid G are given by x1 plus x2 plus x3 by 3, y1 plus y2 plus y3 by 3. So how we can find the coordinate of the centroid? If we know the vertices of all three vertices of a triangle, then we can calculate this point, the coordinate of this point, and that is given by x1 plus x2 plus x3 by 3, comma y1 plus y2 plus y3 by 3. So this is centroid. Okay, so centroid is a point of intersection of medians of triangles. Clear? Next point is orthocenter. So what is the difference between centroid and orthocenter? So the orthocenter of a triangle is the point of intersection of its altitudes. Okay, so the intersection point of the altitudes of a triangle is the orthocenter. So let's suppose we have a triangle ABC and the coordinate of the vertices are A is x1 comma y1, B is x2 comma y2, and C is x3 comma y3. And we draw the altitude from each vertex. And what is altitude? We draw from the vertex A to its opposite side, just like A from BC. And that line, when you draw that line is perpendicular to the side BC. So that line is altitude from vertex A to side BC. So that line is perpendicular to BC. We can also draw other two altitudes from vertex B to side AC and from vertex C to side AB. Clear? So these lines are perpendicular. So from vertex A, that line is perpendicular to BC, and from vertex C, that line is perpendicular to AB, and from vertex B, that line is perpendicular to AC. So these are the altitudes of the triangle, and where they intersect, that point is called orthocenter. Clear? Understand? Any doubt? Okay. So the coordinate of this point, orthocenter is given by the formula, that is x1 tan A plus x2 tan B plus x3 tan C by tan A plus tan B plus tan C, comma y1 tan A plus y2 tan B plus y3 tan C by tan A plus tan B plus tan C. Clear? So this is the formula for orthocenter. Okay. We just recall the formula. We don't go to the proof of the formula because this is a crash course, so we need to recall all the formula. So next point is circumcenter. So next point of a triangle is circumcenter. So what is this? So the circumcenter of a triangle is the point of intersection of the perpendicular bisector of its sides. Okay, that is perpendicular bisector of its sides. So we have a triangle ABC, and the circumcenter is the point of a triangle, and that is a point of intersection that is made up by perpendicular bisector of sides. So when we bisect the sides by a perpendicular line, so we have a side AB and there is a line that is bisect this side AB, and that is also perpendicular to this side, and that is your perpendicular bisector for this side. And where they intersect, so we draw three perpendicular bisector for all three sides, and where they intersect, that point is called circumcenter. Okay, altitude is different with from perpendicular bisector. Okay, we draw perpendicular bisector for sides, and altitude is from vertex. Okay, so it is the center of the circle passing through the vertex of a triangle, and so it is equidistant from the vertex of the triangle. So circumcenter is a point of intersection of the perpendicular bisector of its sides, and when we draw the circle with this circumcenter, that circle is passing through all three vertex. So this circle is passing through A, B and C. So this OA, OB and OC are the radius of this circle. So this all, as this is radius, so this all length OA, OB, OC are equal. So it is equidistance from vertex. That means the circumcenter is equidistance from all the vertices. Okay. So here OA is equal to OB, O is equal to OC, where O is the center of circle and ABC are the vertices of a triangle. And this O is circumcenter. So how we can calculate the coordinate of this circumcenter? So the coordinate of the circumcenter are given by this, that is x1 sine 2a plus x2 sine 2b plus x3 sine 2c by sine 2a plus sine 2b plus sine 2c, comma y1 sine 2a plus y2 sine 2b plus y3 sine 2c by sine 2a plus sine 2b plus sine 2c. This a, b, c are the length of the side. Okay. So by using this, we can calculate the coordinate of circumcenter. So this is the third point of a triangle. Clear? So let's go to the next point. So the next point is incenter. Okay. So what is incenter? The point of intersection of the internal bisector of the angles. Okay. So now the point of intersection is made of by internal bisector of an angle. So we have a triangle, it has three angles. Okay. And when we bisect the angle, that is called internally bisect the angle, that is called internal bisector. And when we draw for all three angles, so where they intersect, this internal bisector intersect, that point is called incenter. Okay. So we have a triangle with vertex ABC, that is given by x1 y1, x2 y2, x3 y3. So for the triangle ABC, the length BC is A, the length CA is B, and the length AB is C. Then the coordinate of incenter is given by, that denoted by I, that is AX1 plus BX2 plus CX3 by A plus B plus C, comma AY1 plus BY2 plus CY3 by A plus B plus C. So this is your triangle ABC, and when we internally bisect the angle, so where they intersect, the point of intersection of this internal bisector of angle, so that point is called incenter. Okay. And we take the length BC as A and the length AB as C and the length AC as B. So the coordinate of this incenter is given by this formula, AX1 plus BX2 plus CX3 by A plus B plus C, and AY1 plus BY2 plus CY3 by A plus B plus C. Okay. So next point is excenter. Okay. So coordinate of excenter opposite of angle A is given by, so we have a triangle ABC. So we calculate, so there are three excenter for each angle. Angle is A, B and C. So how we define the excenter? So the point where the internal angle bisector of one angle and the external angle bisector of the other two angle intersect, that point is called excenter. Okay. So the angle bisector for angle A and the external angle bisector for other side B and C, where the point is intersect, that point is called excenter. Okay. So we can draw excenter for angle A and also for angle B, and there is also an excenter point for angle C. So this is the picture of the excenter point for particular case for angle A, and that point, that excenter point opposite of angle A is given by this formula. So the x coordinate is given by minus A x1 plus B x2 plus C x3 by minus A plus B plus C, and the y coordinate of excenter is given by minus A y1 plus B y2 plus C y3 by minus A plus B plus C. And the similar way, we can also find the coordinate of excenter opposite to angle B and coordinate of excenter opposite to angle C. that is noted by I2 and I3, that is opposite of angle B and opposite C, and that is given by I2. Opposite of B is given by AX1 minus BX2 plus CX3 by A minus B plus C, AY1 minus BY2 plus CY3 by A minus B plus C, and the third ith is given by AX1 plus BX2 minus CX3 by A plus B minus C, and AY1 plus BY2 minus CY3 by A plus B minus C. So that's how we can calculate X center. How we define X center? The point where the internal angle bisector of one angle and the external angle bisector of other two angle intersect. That point is X center for angle A. Okay, that is internal angle bisector for angle A and external angle bisector for angle B and angle C. Clear? And this is the formula to calculate the coordinate of X center angle, center point opposite of angle B, opposite of angle B, and opposite of angle C. Okay. In case of equilateral triangle, so when we take the equilateral triangle, the orthocenter point, centroid point, circumcenter, and incenter all are coincide. So all are coincide. Okay. In case of equilateral triangle, that means all are same. Okay. Clear? Okay. So there is some important result related to points of a triangle. So first one is circumcenter of a right angle triangle. So now we discuss for right angle triangle where the right angle is at vertex A. So the circumcenter is given by B plus C by 2. Okay. Next, about orthocenter. So orthocenter of a right angle triangle ABC is right angle at A, that is A. Okay. Orthocenter, centroid, circumcenter of a triangle are collinear. So if you calculate the orthocenter point, the centroid point, and circumcenter point of a triangle, then these 3 points are collinear. Okay, clear? Important result. Next important result is the centroid divide the line joining the orthocenter and circumcenter. So it first calculate centroid point, orthocenter point, and circumcenter point, and we join the line between orthocenter and circumcenter. So the centroid divide, the centroid is the point that divide the line joining this orthocenter and circumcenter in the ratio 2:1, as these 3 points are collinear. Okay. Next, the circumcenter of a right angle triangle. When we are discussing about right angle triangle, for the right angle triangle, the circumcenter is the midpoint of the hypotenuse. Okay. And in case of isosceles triangle, if any two of its medians are equal. So a triangle is isosceles if any two of its medians are equal. So these are the important result for triangle. Next topic is change of axis. Okay. So first, to alter the origin of coordinate without altering the direction of the axis. So in this first case, what we do, we shift the origin. Okay. And we doesn't change, we doesn't altering the direction of the axis, we just shifting the origin. So as from this figure, the first origin is at 0, 0. So now we shifted this origin to the point A, B, and we does not change the direction of the axis. So the new, when we shifted the origin, the new shifted axis x dash and y dash are parallel to original x and y. That is by moving the x and y axis parallel to themselves. And we just shifted the origin from 0, 0 to A, B. So when we shifted the origin, so the point x1, y1 is the point of point according to the old origin. According to the old origin, when origin is 0 comma 0, and when we shifted the origin from 0 comma 0 to a comma b, then the new point system, that is given by x1 minus a, y1 minus b. So p is the point in this coordinate system. So x1 y1 is the old coordinate system according to when the origin is at 0 comma 0, and when we shifted this origin to a point a comma b, then this same point is given by x1 minus a, y1 minus b. That is, x coordinate is given by x1 minus a and the y coordinate is given by y1 minus b. So in this first case, we just shifted the origin. Clear? Let's go to the second case. Now we change the direction of the axis without changing the origin. Clear? So OX and OY be the old axis, and so what we do, we change the direction and get the new axis, that is OX dash and OY dash. Okay, and how we get this new axis is just obtained by rotating the old axis OX and OY through an angle theta. So when we rotate our old axis OX and OY with angle theta, we get the new axis OX dash and OY dash. Okay, then the coordinate of point P x1 comma y xy, that the point coordinate xy with respect to old system, so with respect to new coordinate axis is given by x dash and y dash, where x dash is x cos theta plus y sin theta and y dash is minus x sin theta plus y cos theta. So that's how we can calculate the point of coordinate for the point P as x1 y1 with respect to new coordinate axis. And how we get this new coordinate axis? We just rotate our old coordinate axis OX and OY with an angle theta. Clear? So x and y are old coordinates and x dash and y dash are new coordinate. Okay, so the axis rotation in anti-clockwise we take is positive, and when we take it clockwise rotation of axis is negative. Clear? Next, to change the direction of axis of coordinated by changing the origin. So now we change the origin as well as we change the direction. Okay, so in this case, if p x comma y and the axes are shifted parallel to the original axis, so the new origin is alpha beta. So at first we shifted the origin, and as we shifted parallel to the original axis, so we just shifted the origin as in first case. So now my origins become alpha beta. Okay, and then the axes are rotated about the new origin alpha beta by an angle phi. So in the third case, we combine our first and second case, as at first we shifted the origin to alpha beta, and then we also change the direction. We also rotate our axis with the new origin alpha beta by an angle phi in the anti-clockwise. Then coordinate of P will be given by this: x is equal to alpha plus x dash cos phi minus y dash sin phi, and y is equal to beta plus x dash sin phi plus y dash cos phi. Okay, clear? So next topic is slope of a line. So how we can define a slope? So the tangent of an angle that a line makes with the positive direction of x-axis. So let's suppose we have a line and we want to find the slope of that line. So let's suppose that line make an angle with positive direction of x-axis, and when we take the tangent of that angle, then we get slope of the line. So tangent of the angle that the line makes with positive direction of x-axis, that is called slope or gradient of the line, and it is noted by small m. So let's suppose the angle made by this line is theta with positive direction of x-axis, then m is equal to tan theta. Okay, so m is equal to tan theta. So what is the formula for slope in terms of coordinate system? So let's suppose we have coordinate of any 2 points from the line, then what is the slope of line in terms of the coordinate of these 2 points? So let P x1 y1 and Q x2 y2 be 2 points on a line that is making an angle theta with positive direction of x-axis. Then the slope is given by m is equal to y2 minus y1 by x2 minus x1. Difference of ordinate by difference of abscissa. So this is the line from this figure. This is the line that's make an angle theta with positive direction of x-axis, and x1 y1 and x2 y2 are the 2 points on the line. So with the help of these 2 points, we can calculate the slope, and that is equal to m equal to y2 minus y1 by x2 minus x1. We can also prove this formula very easily. Okay. Next is parallel and perpendicular lines on the coordinate axis. So when a line is parallel to x-axis, so as this line is parallel to x-axis, so the angle made with positive direction of x-axis is 0. Therefore, slope of this line is tan theta, that is tan 0, that is 0. And when we take the line parallel to y-axis, so line parallel to y-axis mean line perpendicular to x-axis. So when the line is perpendicular to x-axis, that means it make an angle 90 degree with positive direction of x-axis. So its slope is given by tan pi by 2, and that is infinity. Clear? And the slope of a line equally inclined with axis, that is given by 1 and minus 1, because it make an angle 45 degree and 1 or 135 degree with x-axis. Okay, simple. So what is locus? So the locus, it is the path. So let's suppose we have a point, and point is moving. So when we it move, it make a curve, it trace a path. So locus is the path or curve that is traced by this moving point, and that satisfies some certain given condition. Okay, so how we can find the equation of this locus of a point? So equation of this locus or point is the algebraic relation which is satisfied by the coordinates of every point on the locus of the point. So equation to this locus represent a algebraic relation, and that is satisfied by each point that is lie on this path, that is lie on this path, that is lie in the locus of this point. Okay, and what are the steps to find the locus of a point? So first step, assume a point on the locus. Let's suppose h comma k. So assume that coordinate of point say h comma k, whose locus to be find. So we have to find locus of the point h comma k. Then as this point satisfies some certain condition, then write that in step 2, write the given condition involving h comma k. In step 3, eliminate the variables if any other than h and k, and at the last step, replace that h with x and k with y, and that equation you obtained is the locus of the point. Okay, so just wait for a moment. Now we'll practice some question. Okay, so first question is length of the median from B to AC, where A is -1 3, B is 1 -1, and C is 5 1 is. So in this question we have to find the length of median from what, from vertex B to side AC. So we have to find from this figure, we have to find the length BD, that is noted by H. So what is the length of BD? Okay, options are root 18, option B root 10, option C 2 root 3, and option D 4. Okay, so try this question. So as in this question we have to find the length. So that is length is find by the distance formula. So we have to use the distance formula. But to apply the distance formula, we must have the point B and point D. As the point B is 1 comma minus 1. But how we can calculate this point D? So to find D, apply the section formula and then apply the distance formula to find the length of median. Okay. So just try this question. Anyone? Which option is correct? Okay, let's solve. So correct answer is option B, that is root 10. So match with this with your answer. So formula and key points that we use in this question. So the first one is the midpoint formula. So the midpoint, if we have 2 point A and B, that is x1 comma y1 and B is x2 comma y2, then the coordinate of midpoint is given by x1 plus x2 by 2, y1 plus y2 by 2. And second one is distance formula. So if we have 2 point A, that is x1 comma y1 and B x2 comma y2, then distance AB is given by root under x2 minus x1 square plus y2 minus y1 whole square. Okay. So as BD be the median, when we draw the median from vertex B to side AC, that median is BD. And we have to find this BD, the length of BD. So for this, to apply the distance formula, at first we have to find the coordinate of D. And as BD is the median, so D is the midpoint of side AC. So we apply the midpoint formula to find the coordinate of D. And according to midpoint formula, the coordinate of D is -1 plus 5 by 2, comma 3 plus 1 by 2. As we know the coordinate of A and C, so that we get 2 comma 2. So 2 comma 2 is the coordinate of D. So now we can apply the distance formula to find the length of this median. So when we apply the distance formula, we get root under 2 minus 1 whole square plus 2 plus 1 whole square, that is root under 1 plus 9, that is root under 10. So root 10 is the length of a median from vertex B to side AC. Clear? Any doubt? Simple question. Okay. Question number 2. 3 points P plus 1 comma 1, 2P plus 1 comma 3 and 2P plus 2 comma 2P are collinear. Okay. If P is equal to options -1, option B 1, option C 2, option D 0. So there are 3 points. We are given 3 points, 3 points and the coordinate of all 3 points. And if we consider these 3 points as collinear, then what is the value of P? Okay. So what is the condition of a point to be collinear? Okay. So just recall that formula, just recall that condition and try to solve this question. Okay. We know that if A, B, C are 3 points and we have to check either these 3 points are collinear or not, then we consider these 3 points as a triangle and we find the area of that triangle. And if we get the area as 0, then what it implies? It implies that these 3 points are collinear. Okay, so how we can find the area of triangle? What is the formula to calculate the area of triangle? If we know the vertices of the triangle, we have two form. One is algebraic relation form and another is determinant form. Okay, so use any of the form. You get a relation, we get an equation with P, and then you can easily calculate the what is the value of P. Okay, so try. Okay, let's solve together. So correct answer is option C, that is 2. Okay. So we know that 3 points x1 comma y1 and x2 comma y2 and x3 comma y3 are collinear. Then determinant is 0. That determinant is equal determinant of x1 y1 1, x2 y2 1, x3 y3 1 is 0. So we just use this formula to solve this problem. Okay. Now this is a condition of collinearity. So what are the points? P plus 1 1, 2P plus 1 3 and 2P plus 2 2P. So just substitute the value, we get P plus 1 1 1, 2P plus 1 3 1 and 2P plus 2 2P 1 is equal to 0. Now expand this determinant along with row 1 and find this determinant. We get P plus 1 into 3 minus 2P minus 1 into 2P plus 1 minus 2P minus 2 plus 1, 4P square plus 2P minus 6P minus 6 is equal to 0. We know how to calculate determinant. So we get an equation with variable P, that is minus 2P square plus P plus 3 plus 1 plus 4P square minus 4P minus 6 is equal to 0. So from here we get 2P square minus 3P minus 2 is equal to 0. That is 2P square minus 4P plus P minus 2 is equal to 0. So the value of P is 2 and minus 1 by 2. Okay. So for this value of P, these points are collinear. Okay. Question number 3. The point A divide the join of P. P point is minus 5 comma 1 and point Q is 3 comma 5 in the ratio K is to 1. So the point A divides the line joining of this two point P and Q in the ratio of K is to 1. The value of K for which the area of triangle ABC, where B is 1 comma 5, C is 7 comma minus 2 is equal to 2 square unit R. Okay. So in this question, we are given area of triangle, that is the vertex of area of triangle is ABC, where the vertex B is 1 comma 5, vertex C is 7 comma minus 2, and area is given to 2 square unit. And for the vertex A, there is another information for the to how we can calculate the vertex A, and that information is the vertex A divide the line joining P and Q in the ratio of k is to 1. So from this information we have to calculate the vertex A, and when we have the vertex A, then we use the second information from this question, that is area of this triangle ABC is 2 square unit, and by using this we can easily calculate the value of K. Okay, options are 7 comma 30 by 9, option B 7 comma 31 by 9, option C 4 comma 31 by 9, and option D 7 comma 31 by 3. Okay, so try this question. At first find the coordinate A and then use the area of triangle, that is 2 square unit. What is the coordinate of A? Anyone? Okay, let's calculate. So correct answer is option B, 7 comma 31 by 9. Okay. So the formula that are used in this question, the first one is the coordinate of point P which divide the line joining point A x1 y1 and B x2 y2 in the ratio k is to 1 is given by k x2 plus x1 by k plus 1 k y2 plus y1 by k plus 1. So we use this formula to find the coordinate of A. Okay. Second, area of triangle, when we know the vertices of a triangle. So the vertex A is x1 comma y1, B is x2 comma y2, C is x3 comma y3. Then area of the triangle is given by mod 1 by 2 summation x1 y2 minus y3. So we use this formula for second part of the question. Okay. Now, so at first we have to find coordinate of A, and for coordinate of for point A, in the question is given that this point A divide the line joining P minus 5 1 and Q 3 comma 5 in the ratio k is to 1. Okay. So by applying the first formula, we get the coordinate A as 3k minus 5 by k plus 1 comma 5k plus 1 by k plus 1. Okay. So now we have the coordinate A, and as area of triangle is given by the formula 1 by 2 mod x1 by 2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. So substitute the coordinates of the triangle, the coordinates of vertices of a triangle. So we get 1 by 2, 3k minus 5 by k plus 1 7 plus 1 into minus 2 minus 5k plus 1 by k plus 1 plus 7 into 5k plus 1 by k plus 1 minus 5, that is equal to 2, because it is given that this area of this triangle is 2 square unit. And we consider the mod sign, and when we remove the mod sign we get plus minus 2. So we get 1 by 2 3k minus 5 by k plus 1 7 plus minus 2 minus 5 k plus 1 by k plus 1 plus 7 into 5k plus 1 by k plus 1 minus 5, and that is equal to plus minus 2. So when we solve this, we get 14k minus 66 is equal to 4k plus 4, that is 10k is equal to 70. So from here we get k is equal to 7. And when we consider second case, there is two cases, one with plus 2 and one with minus 2. So in the first case we get k is equal to 7, and from the second case we get 14k minus 66 is equal to minus 4k minus 4, and when we solve this we get 18k is equal to 62, that is k is equal to 31 by 9. Therefore, two values of k are 7 and 31 by 9. We get two values because when we take the reverse process of area of triangle, inverse process, we have to consider two cases. We have to take one area is plus 2, another is minus 1. Okay. Next question. So if delta 1 is the area of triangle with vertices 0, 0, a tan alpha, b cot alpha, a sin alpha, b cos alpha. So delta 1 is the area of this triangle with this vertices, and delta 2 is another triangle with vertices. So delta 2 is the area of another triangle with vertices a comma b, a sec square alpha, b cosec square alpha, a plus a sin square alpha plus b cos square alpha, and delta 3 is the area of the triangle with vertices 0, 0, a tan alpha, comma minus b cot alpha, a sin alpha, comma b cos alpha. Then which option is correct? Option A is delta 1, delta 2, delta 3 are in GP. Option B, delta 1, delta 2, delta 3 are not in GP. Option C, cannot be discussed. And option D, none of this. Okay. So in this question, at first we have to calculate all three areas of all three triangles. Then we have to check is the area are in GP or not. Okay. So this is a lengthy question. So let's discuss. Option B, these are not in GP. Okay. The first formula that we use in this question is area of triangle when we know the vertices of the triangle, and that is given by the determinant, and that is equal to 1 by 2 x. First row is x1 y1 1, second row is x2 y2 1, and third row is x3 y3 1. And 3 numbers a, b and c are in GP. Then b square is equal to ac. So at first we calculate delta 1, delta 2, delta 3, and if they satisfy this condition, b square is equal to ac, then this are in GP. Okay. So for triangle 1, so area is delta 1, and that is given by this determinant 1 by 2, 0, 0, 1, a tan alpha, b cot alpha 1, a sin alpha, b cos alpha 1. So when we solve this determinant, we get 1 by 2 AB mod sin alpha minus cos alpha. Okay, so this is your first area of first triangle, that is 1 by 2 AB mod sin alpha minus cos alpha. Okay, mod sin alpha minus cos alpha. Next, for second triangle, that is area is denoted by delta 2, that is given by 1 by 2. Use this formula, substitute the coordinate of the vertices of second triangle, we get 1 by 2 determinant of a b1, a sec square alpha, b cosec square alpha 1, a plus a sin square alpha, b plus b cos square alpha 1. Okay. So we have to solve the determinant, and to solve determinant we apply the operations. So we change C1 by C1 minus AC3, and we change the column 2 with the operation C2 minus BC3. So when we apply this operation, we get delta 2 is equal to 1 by 2 AB 0 comma 0 1 tan square alpha cot square alpha 1 sin square alpha cos square alpha 1. So when we expand this with along row 1, we get area is equal to 1 by 2 AB mod sin square alpha minus cos square alpha. Okay. Now for third triangle, that is delta 3, we get 1 by 2 mod 0 0 1 a tan alpha minus b cot alpha 1 a sin alpha b cos alpha 1, and when we expand this, we get 1 by 2 AB mod sin alpha plus cos alpha. And when you observe this values of triangle delta 1, delta 2, delta 3, as delta 1 is 1 by 2 AB mod sin alpha minus cos alpha, delta 2 is 1 by 2 AB mod sin square alpha minus cos square alpha, delta 3 is 1 by 2 AB mod sin alpha plus cos alpha. So when we multiply delta 1 and delta 3, we get 1 by 2 AB time delta 2. Simple observation. And from here, let's suppose this three areas number are in GP. So it must satisfy this condition, that is delta 1 into delta 3 is equal to delta 2 square. So it means from this two equation, first equation is delta 1 delta 3 is equal to 1 by 2 AB delta 2, and second one is delta 1 delta 3 is equal to delta 2 square. So delta 2 square is equal to 1 by 2 AB delta 2. So from here we get 1 by 2 AB delta 2 is equal to delta 2 square. So when you simplify this, we get delta 2 is equal to 1 by 2 AB. So substitute the value of delta 2, so we get 1 by 2 AB sin square alpha minus cos square alpha is equal to 1 by 2 AB. And from here we get sin square alpha minus cos square alpha is equal to 1. And when we solve this trigonometric expression, apply the property, like what is the formula of cos square alpha minus sin square alpha, that is cos 2 alpha. So when we apply, we get alpha is equal to 2m plus 1 pi by 2, where m is an integer. Okay, that is the value of alpha. But for this value of alpha, the vertex of given triangle are not defined, because there is term like a tan alpha, b cot alpha. And when we substitute the particular value of 2m plus 1 pi by 2, so as we know the 10 pi by 2 is not defined. So for this value of alpha, the vertex of given triangle is not defined. Hence it implies that delta 1, delta 2, delta 3 cannot be in GP for any value of alpha. Okay? Clear? Next question. If the area of the triangle formed by the point 0, 0, 0 and ax square comma 0 and point B, that is 0 comma a the power 6x is 1 by 2 a the power 5 square unit, then what is the value of x? Okay. So there are 3 points and we know the coordinate of points. These are 3 vertices of triangle, and it is given that the area is 1 by 2 a the power 5 square unit. Then what is the value of x? So we have to, at first we have to find the area of triangle. Okay. So as the point is origin and second point is a, that is ax square comma 0, the y coordinate of point A is 0, and the point B is 0 comma a6x, that is y coordinate for this. For the point B, the x coordinate is 0. So how this triangle looks? Is it a right angle triangle? Then how we can calculate the area of this triangle? Okay. So, and then we have to calculate what is the value of x? And options are 1 comma 5, option B minus 1 comma 5, option C 1 comma minus 5, option D minus 1 comma minus 5. So try this question. At first imagine how this triangle look in the Cartesian system if we draw this. Is it a right angle triangle? And if it is a right angle triangle, then how we can calculate the area of a right angle triangle? Anyone? Okay, let's solve. Correct answer is option D, that is minus 1 comma minus 5. So we have area of the triangle OA base 1 by 2 into a to the power 5 square unit. And as we know, this area can be easily calculated by this formula 1 by 2 base into height, and that is we find out the base and height easily by the distance formula. So we get 1 by 2 into a to the power x square into a to the power 6x, and that is equal to 1 by 2 a to the power minus 5. So when we compare both sides, we get x square plus 6x is equal to minus 5. And from here we get x square plus 6x plus 5 is equal to 0. And when we solve this, we get x is equal to minus 1 and minus 5. Okay. So question number 6. The value of k for which the distinct point k comma 2 minus 2k comma 1 minus k 2k and point minus 4 minus k comma 6 minus 2k are collinear is. So consider these points are collinear. Then what is the condition for collinearity? Apply that condition and find the value of k. Options are minus 1 or 1 by 2. Option B only 1 by 2. Option C only minus 1. And option D cannot be found. Okay. So take this question as homework and try to solve. Okay. So in today's class, we discussed about Cartesian system of rectangular coordinate. At first, we will cover some formulas, some theory portion, and then we practice some question based on Cartesian system of rectangular coordinate. Okay. I hope the session was helpful. Okay then, thank you. Try this question. Hello students, in today's lecture we are going to learn about magnetism and matter. This is theory part. Alright, this is our disclaimer. So let's see a trend analysis of the chapter magnetism and matter in JEE main exam according to last 5 years. So we can say the overall weight is 1.7%. If we talk about yearly question distribution, so we can say in 2023 question asked from magnetic properties of materials. Number of questions 1, and students, if we talk about their difficulty level, so we can say question was easy. In 2022 question asked from magnetic properties of materials. Number of questions 1, and if we talk about their difficulty level, so we can say question was average. In 2021 question asked from torque on a magnetic dipole. Number of questions 1, and their difficulty level average. In 2020 question asked from magnetic properties of materials. Number of questions 1, and their difficulty level average. So from this trend analysis we can say magnetic properties of materials are very important concept. Okay, so now let's look at the index of the topics that we are going to discuss today. So first we will discuss current loop as a magnetic dipole. Okay, then we will discuss bar magnet. Then we will study the magnetic field due to a bar magnet. After that we will study bar magnet as an equivalent solenoid. Then we will study about the torque on a magnetic dipole in a magnetic field. Then we will discuss magnetic field lines. Then we will study magnetization of materials. Then we will discuss magnetic materials. Okay, and magnetic materials are mainly of three types, so we will discuss them one by one. First we will study about diamagnetic materials. After that we will discuss paramagnetic materials. Then we will study ferromagnetic materials. Then we will discuss what an electromagnet is. And finally we will discuss permanent magnets. Okay, so these are the topics which we will cover in today's lecture. Okay everyone, so let's start our lecture on current loop as a magnetic dipole. Okay, so the important point here is this: a magnetic dipole means an arrangement where two poles are present. When we talk about a magnetic dipole, you must have here the terms north and south. Yes or no? So we can say a magnet has two poles, north poles and south pole. Okay, so any device or thing on which these north and south poles are present, it means the object on which these north and south poles are present, we can call it a magnetic dipole. Okay, yes or no? Now here question arises, uh, how we know or how we can identify the poles. Okay, so we will discuss it in after some time. Okay, so let's see next concept. If the area of the loop is a, okay, and a equal to pi a square, where a is the radius of the coil, then the magnitude of its magnetic dipole, pm, is the product of the current I and the area, that is pi a square. Okay, this means that the more current flows or the larger the loop, the larger the magnetic dipole moments generated. All right, I is the current flowing through it. Okay, everyone. So if we need to find the current I, then we can rearrange this equation from which we get uh, I equal to Pm divided by pi a square. Okay, so when we rearrange the above equation, this one, Pm equal to Ia, or we can say Ia equal to I pi a square. So when we rearrange this term, you will be get I equal to Pm divided by pi a square. And let this equation first. This simple relation shows how the magnetic dipole moment and the current are related to each other. And the size of the coil also plays an important role in this. And this is clear from this relation equation first. So look at here in the figure, the similarity of the magnetic field patterns obtained due to a solenoid and a bar magnet is shown. Okay, so in this one we have a solenoid, this is solenoid, and this is bar magnet. So there is a, in bar magnet there are two poles, north pole and south pole. All right. So if instead of a circular loop there is a circular coil with n turns, okay, then its magnetic dipole moment Pm increases. In this case, the dipole moment is Pm, which is equal to Nia, and we know the value of A, that is pi a square. So just substitute the value of A, you will be get Pm equal to Ni pi a square. It means that by multiplying the number of turns and the dipole moment increases. Okay, this means the more turns there are, the greater the magnetic field will be, greater the magnetic effect will be. Okay, and the difference between a circular coil and a circular loop is that a loop consists of only one turn, whereas a coil has many turns. Okay, in circular loop one turn, but in coil many turns. Secondly, the formula for the magnetic field at the center of a circular current loop is B equal to mu naught I upon 2A, and let this is equation second. Alright, where mu naught is the magnetic permeability of free space and I is the current and A is the radius of the coil. Alright, so this formula indicates how much the magnetic field will be at the center based on the current and the radius of the coil. In simple terms, we can say as a current increases, the magnetic field increases, and as a radius increases, the magnetic field decreases. Okay, so we can say both these relations are very important for understanding the magnetic properties of the coil, and we know magnetic properties of the coil is a very important for the exam. All right, everyone, clear? So, in this statement, we have substitute the expression for current I that was previously given in equation first into the formula for magnetic field, which is equation second. Okay. So, previously the current was I, that is Pm upon pi a square. Yes or no? And the magnetic field at the center of the current circular current loop was B equal to mu naught I upon 2a. Okay. So, now substituting the value of I into the formula. Okay. So, for B, we get B equal to mu naught upon 2 pi into Pm upon A cube. This means that the magnetic field B at the center of the current loop is directly proportional to the coil's magnetic dipole moment Pm and inversely proportional to the cube of its radius A. Okay. In simple terms, we can say if the dipole moment increases, the magnetic field will also increase. And if the coil's radius increases, the magnetic field will decrease. Okay. Now, this expression B equal to mu naught Pm upon 2 pi A cube helps us understand the magnetic field in terms of the dipole moment, which is the useful for analyzing magnetic properties. Clear, every student? Yes or no? All right. Now let's talk about the bar magnets. So here question arises, what is a bar magnet? A bar magnet can be seen as a combination of two magnetic poles. Okay, so a north pole and a south pole. Here we know north pole and south pole are separated by some distance. In any magnet, the distance between these north and south poles is called the magnetic length of the magnet. Okay, magnetic length of the magnet. So a bar magnet has two important properties. All right. If we talk about the first property, so we can say the first property is the attractive property, in which the magnet attracts its opposite poles. It means the north pole attracts the south pole and vice versa. Okay. The second is the directive property, in which when a bar magnet is freely suspended, it always aligns itself in the north-south direction, just like a compass needle does. Alright, so both these properties demonstrate the magnetic nature of the bar magnet and are important in practical applications. Okay, suppose we have shown you that there is a plus q charge, okay, and a minus q charge. Both are placed separately at a distance of 2L. Alright. Now the interesting thing about a bar magnet is that there are no such charges scattered around here. So to compare this, we introduced a new concept and named it pole strength. Okay, name is pole strength. Meaning, look, in the electric charges and fields chapter, we used to calculate electric dipole moment as q into 2L, that is the charge into distance between two charges. Yes or no? But in case of magnetism and matter, if m is the pole strength of a bar magnet and its magnetic length is 2L, then its magnetic moment is m equal to capital M equal to small m into 2L. Okay, what is the here pole strength? Okay, And magnetic length distance between the poles. Okay, clear? What is pole strength? Anyone? Okay, pole strength is the measure of magnetic pole's ability to attract or repel other magnetic materials. All right. So capital M equal to M into 2L. Magnetic moment is a vector quantity. It means it has both magnitude and direction. Okay. So the direction of magnetic moment is from south pole to north pole. S pole towards N pole. In SI unit system, the unit of magnetic pole strength is ampere meter. Okay, and while the unit of magnetic dipole moment is ampere meter square. Next is suppose if a bar magnet is broken, okay, the small piece formed are themselves as individual magnetic dipoles and not separated isolated magnetic poles. This means each piece carries its own north and south pole. Therefore, magnetic poles are never separated. Okay? So they always remain in dipole form. And this understanding helps in comprehending the basic magnetic nature of a bar magnet. Alright, students? So look at here. This is a bar magnet. A bar magnet is like this as in shown in the figure. We know. And a north pole and a south pole are present on this bar magnet. So look at here, north pole and south pole. So this is north pole, okay, and this south pole. Magnetic field emerges from the north pole and enters the south pole, and internally it travels from south to north and forms a complete loop, okay, as shown in the figure. So in this manner, we can say if we want to study a bar magnet, then first we should know that two magnetic poles are present in a bar magnet, north pole and south pole. Now comes the magnetic field produced by a bar magnet. We have just studied about bar magnets, yes or no? If we need to find the magnetic field of a bar magnet, how will we do it? Let's see. The magnetic field in free space at a point P, which is at a distance r from a bar magnet, uh, it is calculated under two conditions. Alright, one along the axial line and other along the equatorial line. Okay, everyone. The axial line is the line that lies in a straight line between both poles of the magnet. It means in the direction of magnet's length, as you can see in the figure, okay, and the equatorial line is the line that passes perpendicularly through the center of the magnet. So look at here. So this is the axial line, okay, axial. Now the magnetic field at point P, this is the at point P on the axial line, okay, which is at a distance r,
distance r. Okay, here, look at here, from the center of a bar magnet. This is the center, and the distance from center to point P is r. Okay, as you can see in the figure, has the following formula, and the formula is B equal to mu naught upon 4 pi into 2 mr divided by r square minus l square whole square. Okay, so in this formula, mu naught is the magnetic permeability of free space, capital M is the magnetic moment of magnet, and small r is the distance where we are measuring the magnetic field, and small l is the half of the length of the magnet. This means that the magnetic field depends on the distance r, and when we are on the axial line of the magnet, the value of the field is calculated using this formula. Okay, using this formula. And this formula indicates that the magnetic field on the axial line is related to the square of the distance between r square and l square. Now, if we talk about the direction, so we can say the direction of the magnetic field B on the axial line is always along the direction of the magnet's magnetic moment M. Okay, so this means that if the magnetic moment of the magnet is in a certain direction, okay, so the magnetic field also point in that same direction. Okay, right? So now when the magnet is very short, or when we are so far from the magnet that our distance r and is much greater than half of the length l of the magnet, it means r is greater than l. All right, so the formula for the magnetic field can be simplified. Okay, and after simplification, the formula for the magnetic field becomes B equal to mu naught upon 4 pi into 2m upon r cube. Okay, now we can neglect L squared. All right, because its value is much smaller than r squared. This means that when the distance is very large, the magnetic field is inversely proportional to cube of the distance r cube. So this implies that as we move away from the away from the magnet, okay, so the magnetic field decreases very rapidly, and this simplified formula is used for a we can say uh, a short dipole or for distant points. So when the size of the magnet is considered small and we want to calculate the magnetic field, the direction is still in the direction of the magnetic moment. Okay, everyone, clear? Yes or no? Any doubt? All right. Now we will talk about the along the equatorial line. Okay. So the representation of the equatorial line is given in the figure. In this figure, this one is equatorial. Okay, which is a line passing through the center of the magnet and perpendicular to the axis of the magnet. So this one is the axis, okay, and this one is the perpendicular. Okay, so now we have to calculate the magnetic field at point here, or we can say at the equatorial line. So for any point on the equatorial line which is at a distance r as shown in the figure from the center of the magnet, the formula for the magnetic field B is B equal to mu naught upon 4 pi into m upon r square plus l square whole power 3 by 2. Okay, So in this formula, mu naught is the magnetic permeability of free space. Capital M is the magnetic moment of the magnet. Small r is the distance where we are measuring the field, and small l is half the length of the magnet. Okay, everyone, clear? So let's see one special case. When the distance small r is much larger than the length l of the magnet, it means r is greater than l. In that case, we neglect L square, and the formula simplifies to B equal to mu naught upon 4 pi into m upon r cube. This means that even on the equatorial line, the magnetic field is inversely proportional to the cube of the distance, just as it is on the axial line. Okay. However, an important point is that on the equatorial line, the direction of magnetic field B is exactly opposite to the magnetic moment M. Okay. This means if the direction of the magnetic moment is in one direction, then the magnetic field on the equatorial line is the opposite direction. Okay. The difference exists in the direction of the magnetic field between the axial and equatorial lines. Alright. Next is we will talk about in general. Now we need to find the magnetic field at a general point. Okay. As represented in the figure. Look at here. This is general point. When we measure the magnetic field in any direction, that makes an angle theta. Okay. That makes an angle theta with magnet's axis. Then the formula for the magnetic field B is somewhat general. So we can say B equal to mu naught upon 4 pi into m upon r cube into under root 3 cos square theta plus 1. In this formula, r is the distance where we are observing the magnetic field, meaning the distance from the center of the magnetic dipole to the point where we need to find the magnetic field. Okay. And capital M is the magnetic moment of the magnet, and theta is the angle formed between the magnetic axis, that is the line along the length of the magnet. Okay. And the line connecting the center of the magnet dipole to point P, as shown in this figure. All right. This formula indicates that the value of the magnetic field does not only depend on the distance r, but also depends on an angle theta. Okay. So the square of cos theta and its multiplication by 3 affects the strength of the magnetic field. Okay. This means that the magnetic field is different in different directions. All right, everyone, clear? Any doubt? All right. So in these relations, mu naught is a constant which is called the magnetic permeability of free space, and its value is 4 pi into 10 to the power minus 7 Tesla meter per ampere. This constant indicates how the magnetic field will behave in free space, that is, what are the magnetic properties of space. All right. Now we will discuss a bar magnet as an equivalent solenoid. All right, everyone. Now suppose we have a solenoid as represented in the figure, in this figure. Okay. So we can then what will be the magnetic field for that solenoid? Think about it. So we know a solenoid is a coil that often has many loops of wire. Okay, so when current I flows through it, all right, it creates a magnetic field. And the formula for the magnetic field inside a solenoid is B equal to mu naught and I. Here, n means number of turns per unit length. That is how many loops there are per unit per meter or any given length. And I is the current flowing in the solenoid. Mu naught we know is the magnetic permeability constant of free space. So we can say from this formula, we know that the magnetic field inside the solenoid depends on the current and density of turns. Okay. Now, if we want to calculate the magnetic field at a point on the axial line of a solenoid, where the distance of the point from the center of the solenoid is small r and the radius of the solenoid is small a, as shown clearly in the figure. Look at here. So here a is the radius and this is the center. Okay, total length 2L. All right. So we can say then the formula for the magnetic field is follows B equal to mu naught m upon 2 pi r cube. Here capital M is the magnetic moment of the solenoid, which indicates the magnetic strength of the solenoid. Okay, and the formula for magnetic moment is m equal to n into 2L into I into pi a square. So these formulas tells us how to calculate magnetic field inside and outside the solenoid and what the role of magnetic moment plays. So all these formulas are very important for the exam. You need to just remember. Now, if even a single electron is moving in an orbit, okay, then it also behaves like a magnetic dipole and it also has a magnetic moment. Why? Because when the electron orbits, current will develop there and it will behave like a tiny current loop. A single electron that is orbiting in its orbit also behave like a magnetic dipole. This means that the electron has its own magnetic moment which is generated due to its orbital motion. So if we talk about the Bohr magneton, so we can say Bohr magneton is the magnetic moment that arises due to orbital motion of an electron, specifically when the electron is in the innermost orbit, which we call the n equal to 1 orbit. This means that when the electron is revolving in the orbit closest to the nucleus, it has a fixed magnetic moment, which is known as Bohr magneton. Alright. And the value of the Bohr magneton is Mb equal to Eh upon 4 pi Me, which is equal to 9.27 into 10 to the power minus 24 ampere meter square. Alright. And what is E here is the charge of an electron. H is Planck's constant. Me is the mass of an electron. Okay. And this value is very small, but it is very important at the atomic level because it is due to this magnetic moment that the magnetic properties of atoms and molecules are understood. All right. Any doubt here? Yes or no? All right. So now we are going to discuss how much torque acts when we place a magnetic dipole in a magnetic field. Okay. So think about it. Let's see. When a magnetic dipole is placed in a uniform magnetic field, no net force acts on it. It means it does not get pulled forward or backward, but a torque acts on it, which tries to rotate the dipole. So the formula for this torque is tau equal to m cross b, or we can say tau equal to mb sine theta. Here, capital M is the dipole moment, B is the magnetic field, theta is the angle that dipole moment makes with the direction of uniform magnetic field. Okay, so this means when the dipole is slightly tilted from the direction of the magnetic field, the torque tries to align it in the direction of the magnetic field. Okay, look at here. If we rotate this dipole uh, from an initial angular position theta 1 to a final angular position theta 2 as represented in the figure, then students, then work is done in this rotation, and the formula for this work done is W equal to mb cos theta 1 minus cos theta 2. Okay, this means that energy is required to rotate the dipole against the magnetic field. When the dipole is in the direction of magnetic field, its potential energy is low. Okay, and when it is at some angle, the potential energy is higher. All right. So understanding this concept is important because of this, magnets maintain their position in magnetic field and torque aligns them. When a magnetic dipole is placed in a uniform magnetic field, its potential energy UB is equal to the negative dot product of the dipole moment M and magnetic field B. Okay, so what will be the formula? We can say its formula is UB equal to minus M dot B, which is equal to minus MB cos theta. Here, theta is the angle between the axis of the dipole and the direction of the magnetic field. This means we can say when the dipole is aligned in the direction of the magnetic field, it means theta equal to 0 degree and the potential energy is minimum. And when the dipole is in opposite direction, so the magnetic field uh, what maximum magnetic field here theta is equal to 180 degree, so the potential energy is maximum. Okay, so for minimum potential energy theta should be 0 degree, for maximum potential energy theta should be 180 degree. All right, a magnetic compass needle also behaves like a magnetic dipole, which has a magnetic moment m and a magnetic moment of inertia I. Okay, so when the compass needle is released in a magnetic field B, it oscillates around its axis, and the time period t of this oscillation is t equal to 2 pi under root I upon mb. Okay, this means that the greater the moment of inertia of the needle, the longer the time period of the oscillation will be. Okay, and the greater the magnetic moment of the magnetic field, or shorter the time period. All right, now students, we will discuss magnetic field lines. Okay, think about it. What is magnetic field lines? Magnetic field lines are imaginary lines along which a compass needle continuously aligns itself. These lines are used to represent the magnetic field in a region. Magnetic field lines are imaginary lines along which a compass needle continuously align. Okay, these lines are used to represent the magnetic field in a region. Or we can say magnetic field lines are always closed continuous curves. Continuous curve means what? Meaning these lines are circular or loop shaped without any break. Okay, and closed continuous loops mean that the magnetic field lines outside the magnet emerge from the north pole and enter to south pole. Okay, and then inside the magnet they go from the south pole to north pole. If observed carefully, they have no origin or termination point. If we draw a tangent to a magnetic field line at any point, then uh, that tangent indicates the direction of the magnetic field at that point. So now students, an important point is that two magnetic field lines never intersect each other. Why? Why two magnetic field lines can never intersect to each other? Think about it. Because the direction of the magnetic field is unique at every point. If the magnetic field lines intersect, then at uh, a single point there would be two directions for the magnetic field, which is not possible. Okay, so outside the magnet, magnetic field lines go from north pole to south pole, and inside the magnet they return from the south pole to north pole, thus forming closed loops as shown in the figure. These properties helps us understand the behavior of magnetic field. Okay everyone. Now students, let's move towards the magnetization of materials. That is materials like copper, iron, nickel, water, aluminium. Okay, so what are their magnetic properties? The most interesting thing is that you must have always read that magnets attract iron, cobalt and nickel. You have read this. So these are called magnetic materials. But the interesting thing is that besides iron, copper, aluminium, water, nitrogen, all these are also magnetic materials. Okay, when they are placed in a magnetic field or brought near magnets, they exhibit their behavior, and based on this behavior the magnetic materials in your syllabus have categorized three types: diamagnetic, paramagnetic and ferromagnetic. Okay, and we will learn each. Some substances or materials are such that when they are placed in a magnetic field they acquire magnetic properties. Okay, and this process is called magnetization. Okay, and when a when a material is placed in an external magnetic field it becomes magnetized. It means its own magnetic field develops within it. All right. So let's understand. There are some important terms, one of which the magnetic induction or magnetic flux density, and which is denoted by B. Okay. So if the value of magnetic field in space is B naught, then the magnetic induction in a magnetic substance is greater than that. So the formula for the magnetic induction is B equal to mu r B naught. Here mu r is the relative permeability which indicates how much the material gets magnetized Okay, and if mu r is high, think about it, if mu r is high, then the material will be magnetized more easily, and the magnetic field inside that material will also become stronger. All right. Second is magnetic permeability mu. So we can say magnetic permeability mu refers to how easily magnetic lines of induction can pass through a material. It means how easily a magnetic field can pass inside that material. All right. So the magnetic permeability of free space, which is called mu naught, has a value of 4 pi into 10 to the power minus 7 Tesla meter per ampere. All right. But when we talk about a magnetic material, its absolute permeability mu is different, which is different from the permeability of free space. Clear? Yes or no? So for a magnetic substance, we define relative permeability mu r, which is the ratio of absolute permeability. Okay, mu and free space permeability mu naught. So mu upon mu naught is equal to b upon b naught, which is equal to mu r. Students, this relative permeability mu r is a unitless and dimensionless quantity. It means it has no unit. Okay, so relative permeability indicates how much the material enhances the magnetic field compared to free space. If mu r is high, then the material allows the magnetic field to pass more strongly. It means that material is more magnetizable. Now third is intensity of magnetization. So we know intensity of magnetization I means that the magnetic moment induced in a substance upon applying a magnetizing field per unit volume of that substance. That is, it tells us how much magnetic effect has been produced in a small section. Its formula is I equal to m upon v. Here m is the magnetic moment and v is the volume. Intensity of magnetization is a vector quantity. Okay, it means it is also has a direction which is along the direction of the net magnetic moment. Its SI unit is ampere per meter. All right, that is, we can say this quantity helps us understand how much a material has been magnetized in a specific volume and in what direction. So when a magnetic field is applied to it. Clear everyone? Next is intensity of magnetizing field or magnetic intensity H. So intensity of magnetizing field or magnetic intensity H is a quantity that indicates how strong an external magnetizing field is and its capability to magnetize a substance. Okay, and its mathematical definition, or we can say formula, H is equal to b naught upon mu naught, or we can say H is equal to b upon mu. Here b naught is the magnetic field in free space, mu naught is the magnetic permeability of free space, b is the magnetic field inside the material, and mu is the magnetic permeability of the material. All right. So magnetic intensity H is a vector quantity. It means it has a direction and its SI unit is ampere per meter. All right. So we can say this quantity tells us how powerful an external field is to magnetize a material, and it represents the source of the magnetic field. Next is magnetic susceptibility, and this is very important concept. So please note down, denoted by Xim. So magnetic susceptibility is a quantity that indicates how much magnetization I occurs in a substance when a magnetic field is applied to it. Okay, it means that the extent to which that material becomes magnetized as compared to the applied magnetic intensity H. Okay, this means that Xim is equal to I upon H. It is a scalar quantity and it has no units or dimension. It means it is a dimensionless quantity. Clear, students? All right. And all these all these formulas are very important for the exam. Now, there is a relation between relative permeability mu r and magnetic susceptibility chi m. Okay, so when we place a substance in a magnetic field, there is a magnetic flux density which is different from the magnetic flux density B naught in a vacuum. So to understand this relation, we write B equal to mu naught into I plus H, where mu naught is the magnetic permeability of vacuum. Okay, so let's simplify this equation a bit further. So B equal to mu naught H I upon H plus 1. All right. Since I upon H equal to xi m, it then becomes B equal to B naught into xi m plus 1. Okay. So from here B upon B naught equal to xi m plus 1. Now so however we can also rewrite B upon B naught in the form of relative permeability mu r, which indicates how much greater the permeability of a substance in is than the permeability of vacuum. All right. So therefore we write mu r equal to xi m plus 1. This means that if the magnetic susceptibility of a substance is known, then its relative permeability can be easily calculated. Okay, and vice versa. Both these quantities help in understanding magnetic properties. All right, everyone? Yes or no? So let's discuss different types of magnetic materials. We have uh, uh, we have we can say we have classified into we are classified it into three cases. Okay, based on their behavior. So there are three types: diamagnetic material, paramagnetic material, and ferromagnetic material. Okay, diamagnetic material has its own distinct behavior in the magnetic field. Similarly, paramagnetic material and ferromagnetic material also exhibit distinct behavior in a magnetic field. All right. So first, let's observe the behavior of a diamagnetic material. Okay. So when it is placed in an external field, okay, let's see. Diamagnetic materials are those in which, when placed in a strong magnetic field, their magnetic flux slightly decreases. This means that these materials slightly oppose the magnetic field. Okay, so some examples are bismuth, copper, lead, nitrogen at STP. STP means standard temperature and pressure. Okay, water and sodium chloride also. All right, water and sodium chloride are the examples of diamagnetic. All right, in these diamagnetic materials, the net magnetic moment of each atom is zero, which is the sum of the magnetic moments from the orbital motion and spin motion of electrons. When an external magnetic field is supplied, okay, this field slightly distorts the orbits of electrons, due to which a small magnetic moment is produced, which is in the opposite direction to the external field. All right. So because of this, diamagnetic materials are slightly repelled by an external magnetic field, as shown in the figure. Look at here. And these materials tend to move from stronger regions of the magnetic field to weaker regions. All right. So uh, the relative permeability mu r of diamagnetic materials is slightly less than 1. It means mu r is less than 1, and their magnetic susceptibility value is small and negative. So, or we can say diamagnetism is an intrinsic property, it, meaning it is inherent to the material, and it does not change with the variation of magnetic field value or temperature. All right. So all these concepts about the diamagnetic materials. Now students, we will talk about paramagnetic materials. Think about it. Paramagnetic materials are those in which, when they are placed in a magnetizing field, okay, their magnetic flux slightly increases. This means these materials slightly support the magnetic field and allow the magnetic field to pass through them easily. If we talk about the examples, so we can say aluminium, sodium, calcium, oxygen, and copper chloride. Okay, at standard temperature and pressure. In these paramagnetic materials, the net magnetic moment of every atom is not zero. Okay, meaning every atom has its own small magnetic moment. When these materials are placed in an external magnetic field, they are weakly attracted by the magnetic field, and due to this, they tend to move from weaker regions to the magnetic field to stronger regions. Their relative permeability mu r is slightly greater than 1. Okay, that is mu r is greater than 1, and their magnetic susceptibility xim has positive value. So paramagnetism depends on temperature. Okay, so we can say according to Curie's law, this is very important law, The magnetic susceptibility of a paramagnetic material is inversely proportional to temperature. This means we can say this means that as temperature increases, magnetic susceptibility decreases. This relation is mathematically Xim equal to C upon T. Okay, where C is the Curie constant and T is the temperature. Alright, students. Now, students, we will discuss ferromagnetic materials. Okay, this is very important concept. Ferromagnetic materials are like paramagnetic materials, but their special characteristics is that they have domains. Okay, ferromagnetic materials are substances that develop a very high magnetization within themselves in the presence of a magnetic field. These materials give a very strong response in the presence of a magnetic field, which is why they are used to make strong materials. Okay, if we talk about the examples, so iron, cobalt, nickel, gadolinium, and alnico, which is an alloy of iron, aluminium, nickel, cobalt, and copper, okay, are famous examples of ferromagnetic materials. The net magnetic moment of these materials is non-zero in every atom, and the magnetic moments of atoms aligned with uh, each other in a particular direction within a specific region in the absence of magnetic field, as shown in the figure. Okay, so these are called domains. All right, these are called domains. What do domains means? Think about it. So let's compare it like this. Okay, so suppose this is a paramagnetic material. Okay, paramagnetic material, this one. All right, in it the magnetic dipoles are randomly oriented. All right, in any direction. They don't know which way they are facing. There is a no order. They are just lying in any direction. Okay, this one in this figure. So when an external field is applied to it, all the dipoles oriented themselves in a particular direction, and due to which a net magnetic moment becomes apparent. However, in ferromagnetic materials, grouping already exists. This means that a grouping of magnetic dipoles in a single direction is already present. Okay, so as represented in the figure, look at here. Yeah. Okay, so here when grouping already exists, that is the ferromagnetics grouping itself is called domain, and which in which 10 to the power 11 atoms are grouped. So in any one domain, the magnetic dipole moment of all atom is the same direction, meaning meaning the net magnetic moment of 10 to the power 11 atoms in this direction. Okay, in this direction. So when an external field is applied across this material, the domain whose net magnetic the domain we can say whose net magnetic moment is in the direction of external magnetic field starts to expand, and the other domains shrink. But when we apply a strong external magnetic field, all the domains start to merge, and all the magnetic moments present in a magnet in a material, okay, uh, begin to point in a single direction. In a single direction. So we obtained a strong net magnetic moment. So this is the all about the ferromagnetic material. When ferromagnetic materials are placed in an external magnetic field, their magnetic flux increases significantly because their magnetic moments align in the direction of the field. Therefore, their relative permeability mu r is very large. Mu r is greater than 1, which indicates that these materials greatly enhance the magnetic field. Their magnetic susceptibility is also positive and quite high. Okay, which shows a strong relationship between magnetization and magnetic field. All right. Ferromagnetic materials exhibit a behavior with a strong magnetic field similar to paramagnetic materials, but with a much stronger effect, meaning they are very strongly attracted to the magnetic field. Okay, so however, a key aspect is that their magnetic properties also depend on temperature. When the temperature increases, thermal energy begins to randomly, we can say, uh, the magnetic moments of atoms, causing their alignment to break down. Okay, there is a specific temperature known as the Curie temperature, denoted by Tc. So above this temperature, ferromagnetic materials lose their ferromagnetic properties and begin to behave like paramagnetic materials, where their magnetic moment is aligned slightly with an external field. Okay, if iron is heated, okay, and its temperature is raised above the Curie point, that is around 770 degrees Celsius, it loses its ferromagnetic nature and becomes a weak paramagnetic material. Thus, uh, ferromagnetism is a strong magnetic property that depends on the intrinsic atomic structure and temperature, and it is due to this property that we are able to create permanent magnets. Okay, everyone. So, the magnetic susceptibility of ferromagnetic materials varies in this manner. Xi is directly proportional to 1 upon T minus Tc, or we can say Xi equal to C upon T minus Tc. If we remove the proportionality sign, okay, then we get Xi equal to C upon T minus Tc. Here C is a constant and Tc is the Curie temperature. This is also called the Curie Weiss law. This means that when the temperature is greater than Tc, the material starts behaving like a paramagnetic material. Okay? Yes or no? Now we will discuss electromagnets. Electromagnets are typically made in the form of an iron core solenoid, as represented in the figure. Look at here, this one. Okay? When current flows in the solenoid, it produces a small magnetic field. And due to ferromagnetic property of the iron core, the magnetic domains within the iron, which are normally in random directions, align themselves in the direction of that small magnetic field. Because of this alignment, the overall magnetic field of the iron core increases significantly, due to which the magnetic strength of the electromagnets become very strong. In other words, we can say, when current is applied to an iron core solenoid, the ferromagnetic nature of iron amplifies that small magnetic field and create a strong magnet. Okay, so we can say electromagnets are used in many places, such as operations. For example, if something like iron or similar objects has entered someone's eye or nose, then electromagnets are used in a particular way to remove all these things. Okay, they are also used in trains for applying brakes. So this is the all about the electromagnets. All right, everyone. When current flows in an iron core solenoid, the magnetic field increases significantly. Okay, due to ferromagnetic nature of iron, and this effect can multiply the strength of the magnetic field by 10 to 11,000 times. All right. So the formula for magnetic field of a solenoid B is equal to mu naught n I, where mu equal to mu naught into mu r. So we know mu r is the relative permeability of iron, which indicates how much more iron enhances the magnetic field compared to vacuum. Okay, and n is the number of turns per unit length of the solenoid, and I is the current flowing through the solenoid. This means more we can say more turns there are, and the higher the current, the stronger the magnetic field will be. Okay, and with the iron's high relative permeability, this field is further enhanced. Therefore, electromagnets become powerful. So now we will discuss permanent magnet. So substances that retain their ferromagnetic properties for a long time at room temperature are called hard ferromagnetic materials, and permanent magnets are made from these materials. There are several ways to make permanent magnets. An easy and efficient method to make a permanent magnet is to place a hard ferromagnetic rod inside a solenoid and pass current through the solenoid. When current flows through the solenoid creates a strong magnetic field which magnetizes the ferromagnetic rod. This is in through this process the rod maintains its magnetic properties for a long time and become a permanent magnet. Okay? So let's summarize the topics we have studied. First, current loop as a magnetic dipole. Then we studied bar magnet. Then magnetic field due to a bar magnet. Then bar magnet as an equivalent solenoid. then torque on a magnetic dipole in a magnetic field, then magnetic field lines, then magnetization of materials, then magnetic materials, then diamagnetic materials, then paramagnetic materials, ferromagnetic materials, then electromagnet, last permanent magnet. Okay, thank you for your attention. Now students, we will solve some practice questions based on these topics. So are you ready for the practice question? Yes or no? Everyone? Okay, please wait. Now students, we will solve some practice questions based on magnetism and matter. Okay, this is our disclaimer. So here we will solve some practice questions based on magnetism and matter. So our first question, a short bar magnet placed with its axis at 30° with a uniform external magnetic field of 0.16 Tesla. Okay, experiences a torque of magnitude 0.032 joule. The magnetic moment of the bar magnet will be what? So here we will use the concept of torque, which acts on a magnetic dipole in a uniform external magnetic field. So using this concept, we will find the magnetic moment. Okay, so there are four options. Option A, 0.23 joule per Tesla. Option B, 0.40 joule per Tesla. Option C, 0.80 joule per Tesla. And option D, 0. So which option is correct? Please solve this question everyone. You have some time. After that, we will provide the solution of this question. Okay, please solve. Which one is correct? So the correct option is B. Alright, let's see the solution. The torque tau experienced by a bar magnet is given by formula tau equal to mb sine theta. Okay, where m is the magnetic moment and b is the magnetic field strength. Theta is the angle between the magnetic moment and the magnetic field. In this problem, the tau is given tau equal to 0.032 joule. B is 0.16 Tesla. Theta is 30 degree. So sine 30 equal to 1 by 2. We know this. Now substitute the given values into the torque formula. Okay. So when we substitute the value in the given torque formula, you will be get 0.032, this one, uh, then it is equal to m into 0.16 into 1 by 2. Okay. So when we solving this, you will be get 0.032 equal to m into 0.08. All right. So just solve it. You will be get 0.4 joule per Tesla. Okay. This means that the magnitude of magnetic moment is 0.4 joules per Tesla in this situation, which indicates the strength of the magnetic moment that produces the given torque at the specified magnetic field at an angle. Okay. Next question. A bar magnet of length 10 centimeter and having pole strength equal to 10 to the power minus 3 Weber is capped in a magnetic field having magnetic induction B equal to 4 pi into 10 to the power minus 3 Tesla. It makes an angle of 30 degree with the direction of the magnetic induction. The value of the torque acting on the magnet is what? So you need to find the value of the torque acting on the magnet under this condition. The permeability of free space mu naught is given, that is 4 pi into 10 to the power minus 7 Weber per meter, Weber per ampere meter. Okay. Please solve this question. Which one is correct, everyone? You have some time. Okay. Which one is correct? Let's see the solution. So the correct option is A. All right. So here first it is given that the product of permeability of free space mu naught and pole strength m. This means that if you multiply mu naught by m, the result will be 10 to the power minus 3 Weber. This multiplication is done to correct the unit of pole strength, that is given Weber, and Weber, okay, is unit of magnetic flux. Now we want to find the pole strength m. So we will divide both sides by mu naught and we will get the pole strength, which is as follows: m equal to 10 to the power minus 3 upon mu naught ampere meter. Here the unit of meter, unit of m, okay, is ampere meter, okay, which represents the pole strength. The magnetic moment m is the pole strength m, okay, multiplied by the magnet's length, that is 2L. So it will be m is equal to m into 2L. So the length 2L is given as 0.1 meter. So we write m equal to 10 to the power minus 3 divided by mu naught into 0.1. So this means the value of magnetic moment when we solving, we get 10 to the power minus 4 upon mu naught, okay, or we can say value of magnetic moment is 10 to the power minus 4 divided by mu naught. The formula for torque tau equal to mv sin theta. where B is the magnetic field strength and theta is the angle between the magnet and magnetic field. Now, students, let's substitute the values. So it will be m equal to, you know, 10 to the power minus 4 upon mu naught, and b equal to 4 pi into 10 to the power minus 3 sine 30, we know 1 by 2. So expression for torque will be tau equal to 10 to the power minus 4 upon mu naught into 4 pi into 10 to the power minus 3 into 1 by 2. Okay. So let's simplify this expression and we get the value of torque tau as tau equal to 0.5 Newton meter. This means the torque acting of magnet is 0.5 Newton meter. Okay everyone, clear? Alright. Next question. M and m into root 3 are the magnetic dipole moments of the two magnets which are joined to form a cross figure. The inclination of the system with the field, if their combination is suspended freely in the uniform external magnetic field, B is what? So let's understand the question. In the question, magnetic dipole moment m and m root 3 are present. Okay, these are the magnetic dipole moments of two magnets which have been joined together to form a cross figure. Look at here in the diagram. Okay, reassembling a cross shape. Okay, so a cross shape is formed when there is a 90-degree angle. Now the question is, when this combination is freely suspended in a uniform magnetic field, what will be the inclination of the system with the field? This means a cross like figure has been formed. Okay, as shown in the figure. So the external magnetic field also uniform. Now we need to tell what angle the system formed will make with magnetic field. Students, observe carefully the first magnetic dipole moment whose magnetic dipole moment is m. We assume it makes an angle theta with the magnetic field. Okay. Now, if we have to tell what the second magnetic dipole moment makes, then the angle will be 90 minus theta. Okay. So this concept will be used here, and due to both torques the system will become into equilibrium. Okay, so due to magnetic dipoles they will counterbalance each other and form there are our answer will be derived. Okay, so there are four options: theta equal to 30 degree, theta equal to 45 degree, theta equal to 60 degree, and theta equal to 15 degree. So tell me which option is correct. Okay, you have a sufficient time, please solve. Which one is correct? B option. Okay, good, Varsha. Anyone? So the correct option is C. Alright, let's see the solution. So the first equation is about torque tau 1, which is acting on the magnet first, is tau 1 equal to mb sine theta, where m is the magnetic moment, b is the magnetic field strength, and theta is the angle between the magnetic moment of the first magnet and the magnetic field. Okay. So the second equation is about torque tau 2, which is acting on magnet second. The magnetic moment of the first magnet is making an angle theta with the magnetic field, and the angle between two magnets is 90 degree. Okay. Therefore, the magnetic moment of the second magnet makes an angle 90 minus theta with the magnetic field. So the second equation will be tau 2 equal to root 3 into mb sine 90 minus theta. Okay. Here we replaced angle, and sine 90 minus theta equal to cos theta. So when we solve it, you will be get tau 2 equal to root 3 mb cos theta. And for both torques, tau 1 and tau 2 will be equal when the system is in equilibrium. Okay. So the meaning the magnet is in stable position. So we can say tau 1 equal to tau 2. When we equate both mb sine theta equal to root 3 mb cos theta, you will be get tan theta equal to root 3, which is equal to tan 60 equal to what? Root 3. So we can say theta equal to 60 degree. So from this we will get the value of theta, which is 60 degree. This means that the equilibrium occurs when the angle of the first magnet theta is 60 degrees with the magnetic field. Alright, clear? Next question. A coil of 50 tons and area 1.25 meter square is pivoted about a vertical diameter in a uniform horizontal magnetic field and carries a current of 2 ampere. When the coil is held with its plane in the north-south direction, it experiences a couple of 0.04 Newton meter, and when its plane is along the east-west direction, it experiences a couple of 0.03 Newton meter. The magnetic induction is what? Here we need to find the direction between the area vector and the magnetic field, because the magnetic dipole moment is related to the area vector. Okay, so we need to find the value of magnetic induction, meaning the magnetic field B. So given options, option is 0.2 Tesla, option B 0.3 Tesla, option C 0.5 Tesla, and option D 0.4 Tesla. So which option is correct? A, B, C or D? Please solve this question everyone. You have some time. Which one is correct? Find out the correct answer. So the correct option is D. Okay, let's see the solution. Given a coil with n equal to 50 turns, each with an area A equal to 1.25 into 10 to the power minus 3 meter square, and a current I equal to 2 ampere. We first calculate the magnetic moment M of the coil. So the magnetic moment is the product of number of turns, current and area, which is written as M equal to NIA. Okay. Substituting the values, we get m equal to 50 into 2 into 1.25 into 10 to the power minus 3. When we solving this, you will be get 0.125 ampere meter square, which indicates how strongly the coil will interact with the magnetic field. Alright. The next step is when the normal to the face of the coil makes an angle theta with magnetic field B, then a torque tau I acts on the coil. Alright. So the formula for torque tau is tau equal to mb sin theta. This torques align the magnetic moment of the coil with the direction of the magnetic field, and in this case its value is given as 0.04. So let this is equation first. Okay. Now when the coil is rotated by 90°, the angle between the coil's normal and the magnetic field changes, causing the torque to become tau f equal to mb cos theta, which is equal to 0.03 Newton meter. Let this is equation second. So this uses the trigonometry identity where a 90° shift transforms the sine function into cosine. Okay. To find the magnetic field B, we square both torque expression so that the angle theta is eliminated. On squaring mb sin theta equal to 0.04, we get mb sin theta whole square equal to 0.0016. Okay, and let this equation third. So on squaring it will be mb m square b square cos square theta equal to 0.0009. Let this equation 4. So now adding equation third and 4, we get m square b square sin square theta plus m square b square cos square theta equal to 0.0016 plus 0.0009. Okay. So an equation simplifies to m square b square take as a common, so remaining term sin square theta plus cos square theta equal to 0.0016 plus 0.0009. So when we adding you will be get m square b square equal to 0.0025, and we know that trigonometry function sin square theta plus cos square theta equal to 1. That's why here we put 1. Okay, 1, this one. So taking the square root, you will be get mb equal to 0.05. Since m equal to 0.125, we calculate the magnetic field B. So B equal to 0.05 divided by 0.125 is equal to 0.4 Tesla. Thus the strength of the magnetic field in which the coil is placed is 0.4 Tesla. Okay. So D option is correct. Alright everyone. Any doubt? Next question. A magnetic needle of magnetic moment 6.7 into 10 to the power minus 2 ampere meter square, and moment of inertia 7.5 into 10 to the power 7.5 into 10 to the power minus 6 kilogram meter square is performing simple harmonic oscillations in a magnetic field of 0.01 Tesla. Time taken for 10 complete oscillations is what? So here we need to find the time period. As the time for one oscillation is the time period, the question asks for the time for 10 complete oscillations. So we will multiply the obtained time period by 10, and thus our answer will be obtained. Okay. So there are 4 options. Option A 8.89 second, option B 6.98 second, option C 8.76 second, and option D 6.65 second. So which option is correct? Please solve, students. You have some time. Which one is correct? Find out the correct option. Which one is correct? Please think about it. So correct option will be D. Let's see the solution. The time period of oscillation T is given by the formula, that is T equal to 2 pi under root I upon mb. Here I is the moment of inertia, m is the magnetic moment, and b is the magnetic field strength. This formula means that the time period depends on the square root of the square root. The moment of inertia is divided by the product of the magnetic moment and magnetic field, and then that result is multiplied by 2 pi. So when we substitute the given values, t equal to 2 pi under root 7.5 into 10 to the power minus 6 divided by 6.7 into 10 to the power minus 2 into 0.01, and when we performing calculation you will be get 0.665 second. If we want to find the total time for 10 oscillations, now we just multiply the time period by 10. For example, 10 into 0.665, so it will be 6.65 second. Okay, therefore the total time for 10 oscillations to complete is t equal to 6.65 seconds. All right everyone, clear? Next question, match the following columns. Column first and column second are given. In column first, some quantities are given, and in column second, their dimensions or their characteristics are given. So we have to tell which quantity will match correctly with which. You are given codes. For example, if you mark A with 1, it means A of column first matches with first of column second. Similarly, if you mark B with second, it means B matches with second. So you have to see which quantity is a vector, which is a scalar, what is its units, and what is its dimension. So in this in the code you are given 4 options. As you which combination is correct from column first to column second. So which one is correct? Please solve it. This is very simple. Okay, you have some time. Which one is correct? So correct option is B. All right. Let's see the solution. So column first, magnetic moment SI unit is Newton meter cube per Weber. This unit matches with column seconds, number 3. The permeability mu is given in column first is a scalar quantity, meaning it does not have a direction. So only a magnitude. Therefore it matches with number 4 in column second, where a scalar quantity is given. Column first shows the intensity of magnetization I equal to m upon v, which means magnetic moment per unit volume. This is a vector quantity because it also has direction. Therefore, it matches with number second of column second, which represents vector quantities. Okay. In column first, magnetic induction B is given, and its dimension is ml0 t raised to the power minus 2 a raised to the power minus 1. This dimension matches with the number first of column second. Okay. So final answer matching is A3, B4, C2 and D1. Okay everyone. So this is the correct answer. Any doubt? Yes or no? If you have any doubt, please ask. So that's all for the today. Thank you for your attention. Thank you. In next lecture, we will discuss about electromagnetic induction. Okay, everyone. Thank you. Thank you.